and actually maybe toning it down a bit was, what the hell do you know about pre-vegetation, rivers and CO2 sequestration, Jim? Well, the answer is in the last few years I've been very lucky to be involved in a project here at Illinois with a group of people, some of whom are named on the author list here for this talk, looking at CO2 storage, and the target for this has been a Cambrian reservoir, the Mount Simon sandstone. So what I'm going to try and do today in 10 or 12 minutes is just give a little bit of a brief background to our interest in the topic, and maybe try and set the scene for some of the really exciting talks we've got coming in the next 4 or 5 hours. So the background for this, and sort of starting very broadly, these are 2 images from the IPCC special report on CO2 storage back in 2005. We all know there's a whole range of sites worldwide where that are relevant geologically to CO2 storage, that are either planned or underway. This one here is a rather old one now from 2005. And we also know that there are a whole range of different options for storage of CO2, through from storage in depleted oil and gas reservoirs, through to use of CO2 for enhancing oil recovery, through to using deeper, unused, saline, water-saturated reservoir rocks for the injection and storage of CO2. And we also have got a background in knowing that if we're able to sequester CO2 in this way, what we've got to do is to understand the geological context in the reservoirs and the overlying seals and rocks that we're storing CO2. So issues come up such as, in the long term, what's the storage security of CO2? And when we're doing that and looking over time steps from 1 through to thousands of years, we're beginning to look at the potential influence of different types of trapping, through from trapping on a very small scale within mineral matrices, right through to the larger scale, which is more relevant on a shorter time scale. We also know that when we're looking at especially this first structural and stratigraphic trapping, and looking at the spread of CO2, we know that we want to begin to model and predict where the CO2 plume will move and what its path will be. And what I've done today, I'll give a background to this and just say a little bit about the Illinois project here. But what I've done is actually to put 4 papers online from collaborators here, the group at Wright State and a group here down at the Illinois State Geological Survey, that to give background to this and some of the recent work that's been coming out from this project. So hopefully some of these details you'll get more out of from those papers that we put online. So background as regards reservoir age. Here's a map, a relatively recent map of some selected large carbon capture and storage projects across the world, a whole range here. And in red, what we've done is just highlight some of those that have a specifically Cambrian or Cambro-Ordovician context. And the one that we're here in Illinois is this one here, the Illinois Basin Decatur project here, number 7. The work that we've been involved in the last few years for me, and on a longer, maybe 8 to 10 years for a range of other people, has been through 2 projects, one of which is the DOE-funded Center for Geological Storage of CO2. This is a 4-year project that is aiming to generate new models for thinking about how geological storage systems work. And it's essentially a center that's been set up here at Illinois. The project leader, Scott Fraley, here at the State Geological Survey. The geological theme leader is Bob Ritzie at Wright State. Which has been looking at a really collaborative venture, looking at a whole range of different scales of interest, through from pore scale right through to basinal scale, for the disposal and of CO2. And what it's really trying to do is to gain both fundamental basic scientific knowledge of existing CO2 storage technology and identify areas that can be generically applied to other different CO2 storage projects. So what the centre has been doing has been asking maybe 2 fundamental research questions. The first was, how when we inject CO2 into a reservoir, how can we improve predictions of its location and spread? And in the the next phase of the project from really this year onwards, the real focus is going to be how is this injection related to induced microseismicity that has occurred here, and how can we predict and potentially control its occurrence. So those have been the two broad aims, and the areas of study you can see listed below. And what we've been doing as a reservoir scale geology group is looking at a whole scale of different interests, through from diagenetic right through to basinal scales, using both study of core, of well logs, of analog outcrops and potentially modern environments, and then using that in geostatistical and geocellular modeling. Here's the Illinois Basin, and the injection target here is the Cambrian Mount Simon sandstone. It's excuse me, a Cambrian sandstone that's got a total thickness, maximum thickness, somewhere up here of over 2,500 feet. Here's the test injection site here down at Decatur, which we're going to talk about today. And this work has gone on through the IBDP, the Illinois Basin Decatur project, that basically drilled wells there and was responsible for the injection of CO2. And in the last few years, the project that we've been involved in, looking at the storage of CO2. This is the well site down at Decatur in Illinois. It's an ADM ethanol production plant, and so that's where the CO2 for injection comes from. There are 3 wells drilled down to the Precambrian basement at the moment, somewhere around 2,000 meters deep, and there's been about just under 1 million tons of carbon dioxide injected between in November 2014. It was injected at about 1,000 tons per day, I think. Actually a little bit more, sorry. And there's post-injection monitoring until 2017. The stratigraphy of the Illinois Basin here, and you can see the target down here, the Mount Simon sandstone, about 2,100 meters deep. Whole range of Cambrian through to Pennsylvanian Carboniferous strata above. 3 broad, thick seals up here. You can see the New Albany Mercita and the Eau Claire shale. But there are a whole series of smaller seals, both within the Mount Simon and here up in the Mississippian. If we look at some seismic imaging that has been led by Hannes Litteru here at the ISGS, this shows the 3 wells, and this essentially is the lower reservoir facies. So the Precambrian basement is down here. There's a little bit of pre-Mount Simon Cambrian sediment, and I'll say a little bit about in a moment. The Mount Simon is divided up into different units, but essentially the reservoir facies and the injection is down in this Mount Simon A unit down here, and this has been the focus of study. Here's some time slicing looking at the Precambrian topography in the Decatur area with the wells here superimposed. And the significant point here is that there is Precambrian topography here onto which sediments were draped and are interbedded. And especially in the second phase of the project, it's becoming of great interest as to what role that might exert on the location of any microseismicity. Facies near the base of the Mount Simon sandstone. Well, here's the granitic Precambrian basement with Cambrian sediments directly on top onto this beautiful unconformity. Above this, we have a series of pre-Mount Simon sediments, whole series of likely marine sediments, beautiful biotubation in here. Then there's an unconformity that comes through to the Mount Simon sandstone itself, and then here towards the right, we can see the typical sediments at the base of the Mount Simon in the injection zone. So what we've been doing is looking at the facies and the geometry, the stacking patterns, trying to interpret the processes in environments. And I'm not going to say very much about this today. Arian is going to come on and talk about this in his presentation this afternoon. And what we've been thinking about are what are the potential likely analogues for this in the modern, and especially how or if we can use any modern analogues to deal with the facies heterogeneity in these sediments, and how different these Cambrian rivers and systems might be. The overarching need here is to look at hierarchy and heterogeneity. And if we look at the scales in hierarchies and heterogeneities from the basin scale right down through to the diagenetic scale, what we're interested in doing is looking at the role of grain size sorting, sedimentary structures, how that then perhaps controls, dictates, or is influencing diagenesis, and how those link up through scales to not only look at the disposal of CO2 and fluids, but increasingly to look at their geomechanical properties and how that may be linked to injection-induced microseismicity. Some recent research again that we put the links on the website here for you to look at. Is some work done and led by Bob Ritzy and colleagues across at Wright State that has begun to look at the relationship between, for instance, things like grain size and bleach zones. These bleach zones are ones that are relatively poor in diagenetic clay, iron reduction sites that tend to be more quartz cemented and can act as barriers and baffles. Bob's group has begun to look at the relative influence of grain size and how that ties to facies, how that ties through to bleaching, and how this may affect pore-perm relationships through these different groupings.
2 minutes.
The work has also begun to look at the importance of capillary processes in the spread of CO2 and their potential role in dictating the rate of movement of CO2, as well as finer grain seals. So, to sum up, what we need to understand for this project is environments of deposition, how that relates to facies, heterogeneity in vertical lateral, the influence on diagenesis, and how that links both the lithological and the mechanical characteristics which may have a great influence on injection-induced microseismicity. But I think this is the segue for the rest of today, is what we really are interested in is how different were these pre-vegetation rivers and floodplains compared to their later successors, and how may those differences in properties affect the geomechanical properties of the sediments and the movements of fluids through such sediments in the Mount Simon sandstone here in Illinois. So that's all I've got to say today, and hopefully, looking forward to the range of talks that hopefully give us some indications into how different these Precambrian rivers are and what the implications might be. Thank you.
Thank you very much, Jim. That was a very good introduction, very good to know all the reasons as to why we need to be looking specifically at this rock. At this time, I think a lot of people are figuring out how to pose questions. There is, if you're looking at a tablet, there is a question mark symbol that you can use to type in a question. If you're at a normal computer, then you can use the question toggle on the right-hand side in the panel to pose questions to the speakers. What I'll do at the moment is post a poll so people can tell us what their expertise in fluvial sedimentology is. So this is an interactive part of this online conference. Feel free to tap in what your experience is. I see there's a large number of academics, but a large number of graduates as well. There we go. Right, if the last people vote on what their experience is. All right. So the experience of the people that are tuning in right now, which is a little over 60 people. So largely academic, but we have a large number of people that are from industry as well. So it's very good to see that there is interest and interest in the pre-vegetated river systems from multiple groups. Another one, poll that I would like to pose is how easy it was to join this particular conference. I noticed that a lot of people were sort of starting to attend at the beginning over the first 3 minutes. It's a delight to see that most people found it extremely easy to join.
Attendees only. How do I get rid of this?
Yeah, the staff members cannot join us on this one. Okay. At this time, I would like to invite Daryl Long, our keynote speaker, to provide us with a background on pre-vegetation river systems, which he has spent a significant amount of time studying those. Here we go.
Okay. Webcam closed by organizer. Show my screen. Share my webcam.
Window for now.
Not working. Okay. Now I've got to find them.
There we go. We've got full.
Okay. Well, that should show my title. And good morning, good afternoon, and good evening, depending where you are in the world. I'm going to talk today about rivers before the advent of land plants, because they have had a significant effect on the distribution of fluvial styles. Okay, why isn't this changing? Okay, there we are. To begin with, let's start with some pre-concepts of what is going on with pre-vegetation systems. Most of these are very thick, very uniform. They lack a lot of aquicludes, so the permeability and porosity should be relatively uniform laterally and vertically. That's if it has any porosity, because many of these sequences are cemented quite tightly and probably would not represent good reservoirs for CO2. One of the basic conditions for rivers before the end of the Silurian is essentially there are no rooted land plants, and these lead significantly to the stabilization of banks. And initially we thought this was absolutely essential for the formation of meander-type things. Another factor is that when it does rain, the water comes off a lot faster. It doesn't get slowed down on the way down the slopes and percolate into the bedrock or the substrate so quickly. So in wet climates, we'd probably have as much as 4 times the rate of discharge from the same amount of rainfall. At the same time as this, there's very limited soil formation because there's no organic acids in the system, or there are limited organic acids that are associated with microbial life, which is certainly present in most of these sequences. So the amount of mud that is present in these systems is quite low, particularly in the Paleoproterozoic, and it seems to increase slightly as we go up through the section, but it rarely exceeds 4 or 5% of the total sequence, and in many of the Paleoproterozoics, it's less than 1%. Another thing that we have to consider is preservation potential, particularly of overbank fines, which tend to be blown away. If you stand on a modern sand plain, you'll probably get a lot of dust in your face. So there's aeolian winnowing. It takes the mud out of the system blows it away, and it gets fixed in shallow marine systems. So there's that problem too. There's the other problem of really we only get thick sequences where we have high subsidence. So we need a tectonic setting where there is continued subsidence. Typically, they are either in rift basins, fallen basins, or passive margins. We don't tend to find fluvial systems outside of those settings because they're weathered, they're removed. Another factor which is very different from modern systems is that the possibility that some of the channel systems are much greater, possibly in excess of 25 kilometers, in the case of some up in the Arctic, which Rob Rainberg has described. And they're dominantly braid plains in these settings, which is a very distal setting. But there also may be a high contribution of distributary fluvial systems rather than isolated ones. One of the big problems that we have as pre-vegetated sedimentologists is that we're not really confident that any of the formulas which have been established so nicely for modern systems really work because of these changed conditions. The modern slope discharge relationships, paleohydrological relationships, we try them tentatively, but the reality is that they probably do not apply, and we need some more work on that. When we come to looking at river systems in the modern, we tend to go by planiform. And if you remember Andrew Miles' work, he established about 16 basic planforms. These have been added to quite significantly since 1996. We have at least another 5 varieties of anabranching rivers. We also have tropical rivers, which Chris Fielding has been discussing recently. So let's take a look at what we can see in the Precambrian. One of the main clues that has been used in the past is the vertical sequence model. And this is all very good. And when you look at the modern systems, again, this is from Andrew Miles' work, you'll see that the black stuff is quite important. That is the muck. And in most Precambrian systems, certainly the early Paleoproterozoic ones, less so in the Cambrian and Cambrian Ordovician, is that the black stuff is essentially missing, typically blown away because there's nothing to fix it. No microbial binding or very limited microbial binding. So it's susceptible to aeolian removal. The way that we get around the problem of not having perfect planform exposures is to attempt to use the architecture of the deposit. And we can do this in cases where we have reasonably large lateral continuity. The basic concepts which were initiated by Alan's work on the Devonian and expanded by Mile and Jordan and Pryor give us a way of breaking down our stratigraphic sequences into various scales, which we refer to as architectural elements. And when we start looking at Precambrian systems, we can recognize quite a lot of these. We can see channels, which can be ribbon or sheet or crevasse channels. We can see gravel bars. We can see sandy bed forms. And these sandy bed forms are the dominant form of most Precambrian systems. And they can be trough or planar or horizontal or upper flow regime type material. Sheet elements, which can be extremely wide, and these could be overbank or they could be confined within channels. Generally, you have real difficulty telling the difference between these two because you would need outcrops in excess of 1 kilometer wide. One of the things that is recognizable that we see also in the Phanerozoic forms are abundant downstream accretionary macroforms. So big channel bars that are depositing on the downstream end, and they're behaving as normal braid bars do in large Phanerozoic river systems. Typically, downstream accretion, the cross beds point in the same direction as the second and third order bounding surfaces. In a few cases, we find evidence that they're migrating up the back of these in-channel bed forms. We can refer to these as upstream accretionary macroforms. We then have lateral accretion macroforms, which are the key indicator for channel sinuosity. In post-vegetation systems, these are the typical features of meandering river systems. However, in the Precambrian, we don't tend, except in one or two examples, to get these lateral accretion surfaces characterized by mud drapes. That's extremely rare. The lateral accretion surfaces, quite common, and if we look at the elements within those, we can see whether they are pure lateral accretion, downstream lateral accretion, or upstream lateral accretion, depending on the relative orientation of crossbeds to the bounding surfaces. We find scour hollows. These are relatively rare, particularly in the early systems, becoming more common as we move up through the Proterozoic and into the early Phanerozoic. Typically, these are interpreted in terms of flow confluences. So their absences or general deficiency is kind of surprising in these systems. We also find sediment gravity flow elements, laminated sand sheet elements, and very rarely overbank flood deposits or fines or soil horizons. When we look at Andrew Miles' models, we can immediately take about 5 of these varieties out because they rely too much on bank stability. Nobody has recorded the fine-grained ones, or the anastomose ones, or the single-channel ones, but there are very few single-channel ones, even from the modern and the branching systems as yet. So let's take a look at some of these systems, beginning with the coarser end of the system, the gravel bed rivers with debris flows. These typically give vertical profiles which make it very difficult to tell the difference between transverse and longitudinal systems, i.e. are you dealing with fans or lowland feeder systems. The basic models require essentially the presence of upper flow regime conditions or debris flow concentrations within the system. You can see here in this example from the Paleoproterozoic, this type of river is characterized by a mixture of normal stream flow deposits and debris flow deposits. Down here we can see a bit of imbrication, which is a good indication that we have, at least at the end of this system, some normal fluid flow processes. But up here you'll notice a predominance of horizontal lamination, indicating that that is probably deposited by some form of hyperconcentrated flow. The mud content in these, incidentally, is less than 1%. When you look at thin sections, you do tend to see a higher amount, and that's usually because the feldspar is weathered to produce pseudomatrix, and this gives you a false appearance of mud. There are no mud drapes. Hyperconcentrated flows can be identified in some cases by inverse coarse-tail braiding, and we can see that here in this example from a fan, alluvial fan system from the Lorraine Formation near Galgander, Ontario, and it shows a distinct coarsening upwards, low matrix content. It's still a class-supported, very thin sand units, probably upper flow regime sand units, separating events. Into the first unusual system. This is from the White Inlet Formation, and this shows clear evidence of hyperconcentrated flow deposits, namely that we've got weak horizontal lamination in some of the areas, and we have a general coarsening upwards in a lot of elements, and these strange, upright, vertically stacked boulders that clearly indicate that we're dealing with large hyperconcentrated flow or debris or dilute debris flow type situations. The same system, but here without the large class, we see again It's what appears to be relatively coarse-grained. You see the pebble sizes here, gravel bed system, and again, inverse coarse-tail grading in a lot of the units. So these probably all represent hyperconcentrated flow deposits, whereas the more uniform, unimodal distributions that we see down here probably represent normal flow regime conditions. And some support from that comes from the presence of cross-bedding in some of these finer pebble grade material. Same thing, this is alluvial fans from a recent paper in the Journal of Asian Earth Sciences. This is from a fan system, scree, but we can see inverse coarse tail grading in these. Again, debris flows a prominent thing. So one of the key factors is going to always be doing your studies on a large enough scale that you can work out the large scale geometry of the systems as well as the small scale architecture. Shallow braided river systems are dominated by gravels, which can be massive, planar cross bedded, or laminated in this case. I haven't seen too many of those, so this is my only picture of one of those. Deep gravel bed rivers show a little bit more characteristic. Typically, these are more than 3 meters deep. The modern systems typically have stepped floodplains. They're usually incisive into floodplains, so that we get a lot of overbanked material trapped up here. But we don't see any of this preserved in our pre-Cambrian examples. This is an extension of the Copper Harbor conglomerates from the Kiewit Island from Lighthouse Point. And if we look at it, we can see some very large clasts and boulders, which must have taken quite a lot of flow, probably again hyperconcentrated flow, but less evidence for this in the system. And then the normal stream deposits between it, which are small pebble grade. When we look at the architecture, we can see a variety of forms that probably indicates some channeling, some lateral accretion going on, but in several directions. So these are just basically stacks of small braided channels. So it fits fairly well with some of the coarser grained braided stream models from the Phanerozoic. What is different, though, is that the fine grain material is not ripple laminated. It is typically upper flow regime, plain laminated with current lineation on the top of it. There are low flow conditions in these channels when they're not capable of moving cobbles and pebbles, which you can see have a slight imbrication in here, is still upper flow. And this is consistent with this very rapid runoff condition and the characteristic that Shum suggested in 1968. Gravel bed meandering systems are a little bit more rare. This is an example from the upper part of the Uralian Formation in Roraima. Very interesting because it contains both gold and diamonds in the base. And they typically occur near the bottom of the system. This is the contact between the lower and the upper member of the Uralian. And this is what is probably a meandering gravel bed river system. Unfortunately, I don't have a lot of architectural slope element measurements on this because I only had 15 minutes to look at this. But it's largely small pebble grade material, and we can see a trough and planar cross beds and massive units within it, as well as a lot of blocks that appear to occur as a result of erosion of this underlying strata. The underlying strata is typically fine grained, but it is not related to the overlying channel. This is a major regional disconformity surface. So we can't say this is anything other than an incised channel. So the question becomes, well, is this really meandering, or is it simply an attached bar form in an incised river? Well, we do see clear evidence of meandering is in the early Cambrian Mount Terry conglomerates of Tatatuja, or the Olgas in the central Australia. And this is wonderful exposure, but unfortunately, due to cultural restrictions, you're not supposed to climb on it. When we look at it close up, we find that there are a large set of 4 to 5 meter packages of cobble conglomerates with low angle inclined stratification separating them. And these appear to be stack upon stack upon stack of attached of lateral accretion sets, suggesting this package of conglomerates was deposited from some form of meandering system. And unfortunately, I can't work out a sinuosity for this because I, again, couldn't measure any surfaces. But when it comes to gravelly, sandy meandering systems, this is one of the first that was described, and the early Proterozoic Tarragon sandstone in Australia is often cited as an example of a pre-vegetation meandering system. But when we start to look at it in detail, it isn't. This type of system appears to be a stack of a coarse system, a sandy system, and then some form of muddy system, which could be a marine incursion. We don't know. There's no architectural detail. The larger scale composite foreheads you see in the top 4 meters, which are in this package in here, show some form of lateral accretion, but it doesn't go through the whole system down to the conglomerates. So we could be dealing just with simple stacking of fluvial systems with progressively reduced fluvial input through time. So knowing a little bit more about the structural context of this, whether it's a transverse or an axial system, would probably help us to understand. Alternatively, one of you can go and look at this. Back to the White Inlet Formation, where we have very clear lateral accretion surfaces. These are the purple lines that go down here. We see quite an interesting sequence because there are piles of conglomerate at the bottom, but also in packages on the top of some of these lateral accretion surfaces. Now these represent what Paul Carling has referred to as boulder berms. Here they are, up here, up here. The sands in here are predominantly planar laminated, but there are also some larger scale, apparently cross-stratified units. When we look in detail, we see some upper flow regime conditions with convex up sandstones, massive sandstones with supported pebbles, and flat lamination. When we look at the geometry of the foresets compared with the geometry of the lateral accretion surfaces, we can separate this whole package into an alternating sequence of units which are dominated by lateral accretion and dominated by downstream accretion, all within this large-scale lateral accretion system. But that doesn't make this system a meandering system sensu stricto, because it is incised into bedrock, and these could simply be attached bars with high sinuosity, which are developed downstream from a bedrock high. Here we see some of these berms coarsening upwards, indication of upper flow regime conditions. In these cases, vertical crafts as well, and little packages on the top. So these are probably very much like the modern streams in north of England when they're subjected to very extreme floods. Mud content, again here, less than 0.5%. There's no mud to support these systems. They're entirely deposited under upper flow regime conditions and the upper part of the lower flow regime conditions. Coming to the another type, sandy meandering systems, been quite a few of these described so far, and in the modern systems, Phanerozoic systems, a lot of mud. In the Proterozoic systems, not so much. These are from Catherine Group in the Mackenzie Mountains, large scale, and the foresets on these are again characterized predominantly by upper flow regime planar lamination with current lineation. You can see throughout this sequence, which is about 1.5 kilometers or so thick, lots of these channel systems with a scale of anywhere between about 4 meters and 15 meters. When we start to look at them in detail, And some of you will recognize the Nelson head from the top. The bottom one is from the upper part of the Catherine group. When we measure all the crossbeds and their thickness and apply Miles' technique for determining the sinuosity of fluvial systems, we get a sinuosity of 1.65. So we certainly have evidence that these are highly sinuous systems, and because they're stacked so consistently, we consider them to probably be meandering as well. There's another meandering system, or a lateral accretion surface. This one I could trace for about 500 meters laterally. It's about 8 to 10 meters thick, and we have large-scale lateral accretion surfaces with current lineation on them, and eroding in the bottom of this some of the very rare overbank silty, sandy mudstones. Not really mud. These are more siltstones than mudstones. The base of this sequence has corrosion furrows produced by turbulent meanders or roll vortices under upper flow regime to transitional conditions. And we actually have a real linkage. Am I running out of time? Ephemeral systems, a bit more rare. I don't have any real records for these of a single channel. But ephemeral conditions are probably indicated in the Precambrian record by the abundance of intraclasts, because typically these will break down within 300 to 400 meters of where they're eroded from an in-channel mud or from a channel wall mud. Fine grain meandering, some have been recorded based essentially on vertical sequences, but there is no architecture for these. And in some cases where we have fine haploid packages, as described by Sonderholm and Tersgaard in '98, they found that these were essentially upper flow regime fluvial systems, and there was absolutely no evidence in these distal fluvial systems for meandering. Probably the most common type is a shallow triennial, which gives you stacks of planar cross-bedded or trough cross-bedded stratification. And we can have simple bars, compound bars, lots of fun measuring these things. And we can also have lateral accretion surfaces. There's the top, and we can have these. We can see this are moving down the system. We also see compound bars with trough cross beds migrating and cascading down the front of our downstream accretionary elements. Downstream accretionary elements are quite common. In this case, they're typically in sets 1 to 2 meters deep. And this is in a sequence which is about a couple of kilometers thick at this particular locality, and incredibly uniform piles and piles of very uniform sand. Another example, this is one that has got a little hollow element up here. This is from the Adam Sound Formation in Nunavut. And again, downstream accretionary components are dominant in this system. One of the big myths of Precambrian sedimentology is that braided streams are sheet braided or dominantly sheet braided. And Cotter defined these as being characterized by uniform thicknesses of trough cross-stratified sandstones. And we can see that one side here, very shallow system, is about 40 centimeters thick with some ripples on the top. And when we look at it laterally, we can trace it for 20, 30, 40, 50 meters, but they are in distinct channels. The channel margins have dips as low as 7 degrees. So that's the high slope is 7 degrees. So it's understandable when people do not find these in the record. But the grain size is uniform throughout the whole system. There's no mud here whatsoever. Going to deep perennial braided systems, this is systems which are probably at least 3 meters deep, and we can find downstream accretionary surfaces, lateral accretion surfaces, and lags, as well as small foul leg ripples that are moving around the end of bar forms. In this particular sequence from the Athabasca Basin, I found the first clear evidence of triennial flow rather than periodic flash type style flow, in that there are discrete bar growth indicated by addition of unit bars, essentially. This is quite uncommon in the Proterozoic river system. Shoot bar in the top. But these are all basically moving in the same direction. It's transverse. And just the detail of that, see there's an obsessive number of measurements. The top of this channel system, these channel systems, characterized by upper flow regime conditions. The falling stage is on the bar tops is allowing us to accumulate granules. So the granules are accumulating on the top of the system and not at the bottom of the system, which is sort of counterintuitive. Looking at the sinuosities, here these are relatively low, using again the mile system. Sinuosities of around 1.1 are atypical of these deep systems, which are estimated to be between 3.2 and 5 meters in thickness, based on the preserved amount of sediment. Now we come to some more exotic types, the high energy sandy braided systems. And these are characterized by sinusoidal bedding. So we're getting into transitional to upper flow regime conditions. These examples are from the Helena Formation in the Belt Supergroup. One of the key factors that you see are these concave up style crossbeds. These are from the Mackenzies, and this type of upper flow regime channelized deposit should be full of upper flow regime conditions, either current lineation, low angle, or these sinuous sediments. Similar situation here, recently described in Journal of Sedimentary Research by Lowe and Arnott from the Potsdam, which I thought might be appropriate for you Cambrian guys. Stacks of upper flow regime material separated by lower flow regime cross-stratified, planar cross-stratified material, and some laminated sheet elements, which they're interpreting as wind rework terminal splays, which is a possibility. Sheet flood distal braided. These are typically characterized by relatively small scale, 10 to 20 centimeters, superimposed flood cycles. Again, the presence of intraclass should be a common feature. Martin's Neo described as massive, the planar to ripple laminated. Other models have trough as well, so these can be quite complex. Flashy ephemeral, very similar in terms of the style, or originally known as a Bijou Crete style, characterized by alternating sand, which can be massive or plain laminated, and very thin mud drapes. And in this case, you can see those thin mud drapes in here in the Manitou Falls Formation, but we can also see these very large blocks or clasts, lone stones, that indicate that we're getting deposition from upper flow regime conditions. Stacking these, there are the muds, still less than 1% of the whole package, but they may produce some vertical heterogeneity in terms of fluid flow. And overbank deposits, these are quite rare. Now, Phil Frelick will be talking about these in more detail later, but one of the problems that we have with overbank deposits is, one, their preservation potential, and two, where they're actually preserved. Are we really looking at overbank deposits, or are we looking at infill of abandoned channels, which is probably the case when we get these thick packages shown here from the Mackenzie Mountain Supergroup, about a meter and a half thick, and we can see some nice little downwards tapering cracks in these systems, which are very different from the syneresis cracks that go up and down, which probably indicates these are deposited underwater. So what now? And this is, what will you guys have to do? And the answer is much more detailed architectural observations with lots of detailed measurements of surface inclination. We need this in order to confirm the depositional style. We need more studies on the relationship between bed forms and paleohydraulics in the absence of vegetation. We also need these studies on terms of basin shape and scale. Are we dealing with transverse or longitudinal systems? We still have to answer the question, why are pre-vegetation river deposits typically so uniform throughout great thicknesses? And this applies much more to the earlier Paleoproterozoic than it does to the early Phanerozoic. We need to answer the questions, what is the role of climate and tectonic setting in controlling fluvial style? The next one is particularly applied to the lower Paleoproterozoic. Why are aeolian deposits not more common? But the only evidence we have in the late Archean and early Paleoproterozoic fluvial systems is gold toroid. So there's a little discs of gold with flattened edges. That's our only indication that aeolian activity is happening. And if you don't have gold in your system, you're out of luck. Another thing we need to consider is, are we dealing with incised or unconfined rivers? The thicker sequences are probably unconfined, but many of the sequences I've shown you today are in incised river systems. And even within thick packages, we probably have drop in base level, which allows us to develop channelized surfaces in the older alluvium and constrain the later systems. And this may lead to a rise in the abundance of lateral accretion deposits. So how do we determine slope, sinuosity, preservation potential? Why are there so few hollow elements? And how on earth do meanders form without bank stabilization from vegetation? Do we require early cements? Do we require salts? Or do we require other as yet unknown processes? Well, perhaps the only answer to this is to go out and look at more rocks, and not just on Earth. I think we can perhaps go off planet, and some of you may be able to go and look at these deposits on Mars and Venus, etc., for yourself. Thank you. All right. Over to you guys.
Thank you so much, Daryl, for that presentation. We've got at least two very interesting questions. The first question I would like to pose is, what are the largest and deepest pre-vegetation rivers that have been found, and what channel pattern might they have? Is there a link there as well?
Okay, the largest, it's the channelized systems, the entrenched systems are probably the deepest. Some of those that Alepi has described and Rainbow have described, probably as much as 20 meters in thickness. But they could be just stacked within incised channels. It's very difficult to tell from the remote sensing pictures that they have of those, how they actually behave. And I think the lateral accretion surfaces in those are probably related to the fact that they're within incised channels. Aerial extensive, these things can be thousands of square kilometers. So the Athabasca is absolutely massive. So that's probably the largest, but it's not the deepest. And those are only 4 or 5 meters deep. The Mississauga channels, which is 1.5 to 3 kilometers of sandstone, over 400 kilometers lateral extent, across strike, is the average channel there is between about 2 and 4.5 meters, based on the cross bedding. And that's very iffy whether we can actually use the preserved thickness of cross beds as an accurate measure of channel depth in the Proterozoic. Again.
Okay. Could you elaborate more on the channel patterns? Because you've shown quite a diverse range of the types of channel patterns that have been seen. is there a distinct change in there? And that's basically a decent segue to a question that was posed by Maria Aspiros, who was asking about the similarities between pre-vegetation river systems and submarine flows, whether or not we should be looking at those as a comparison.
That's a good point. The scale is probably fairly similar because those can be kilometers wide. The big difference is that in the submarine systems, we do have stabilization within the channel by mud silt grade material. And this probably still applies in the Proterozoic, because we will still have those muds that are blown by winds into the sea and remobilized down the slopes. You certainly get lateral accretion deposits. You certainly get planar crossbedding within submarine channels. A lot of the features are known. In terms of the general planiform style of Precambrian rivers, they are predominantly braided. This talk has shown quite a few of the other types because, of course, they're the ones that attract the attention, because one of the main initial attractions of Precambrian rivers is they're incredibly uniform and boring and require a lot of repetitive measurement. So I'm glad that comes through.
Jim Best, did you want to also mention a few things on submarine versus subaerial river systems?
Yeah, but thanks, Aaron. You know, I think it's an interesting point. I suppose complexities that also may come is just actually, you know, I know the jury is still out of this, and there's still a lot of debate in the submarine community on this, is what the differences in processes may be between you know, submarine channels and subaerial channels, just in terms of the difference in fluid dynamics, so in terms of what's going to happen to the water surface slope, what's going to happen to development of thick overbank levees, what may happen to the sense of secondary circulation within meander bends in submarine situations, that may also give a different potential of bark architecture and also style of migration. So I think there's merit to that, but I would sort of also think that it's important to think about the differences in processes that may be inherent between a submarine and a subaerial meandering system.
Right. Thank you very much. I will spend a little bit of time putting one more poll out, which is why are people interested in pre-vegetation river systems, to the panel. And unfortunately, the panel cannot vote, but I know why you're interested in this. So if the people that are attending can let us know how they are interested, whether it is because they have a general interest in planetary geology, or whether it is related to their own work in pre-vegetation age sedimentary deposits. All right. Thank you very much. 75. Most people have voted. There's a few more. They can vote if they want. All right, so most people are interested in rivers and fluvial sediments in general, and are clearly using this as a context for thinking about river systems, which is what many of us are doing as well. That is well over 60%, about 40% is interested in the role of vegetation. We will take this kind of information forward and bring it over to the ICFS, the International Conference on Fluvial Sedimentology, which will be next summer in Calgary. Don't miss it. So that is good information. At this point, I would like to ask Phil Freilich, the next presenter, who is going to talk to us about floodplains and floodplain sediments in particular, which he has fantastic information on.
Okay, we're on air.
Yes, fantastic. Visible and very audible.
Exactly. Seems to have killed my slideshow presentation, but I'm pretty sure I can get that up in a second. So we're going to talk on floodplains. I'm glad I'm not talking about channel systems, because trying to follow Daryl, which was just a great presentation on pre-vegetation channels, would be extremely difficult. So I'm going to talk about something totally different. And I'm going to talk about wet floodplains. There are lots of analogs for dry floodplains, because in the modern, if some place is very, very dry, it's not going to have much vegetation generally, and we can use it as an analog for the past. So dry floodplain analogs exist. They're very similar to desert situations that we see today. However, wet floodplains are quite different today than they were in pre-vegetation times. Now let's see if I can get my slideshow up here and have a look at it. And we'll try. That's a good point. There. It should be up now, I hope. And we'll go to slideshow from beginning. There. Hopefully you can see it. I'm going to go from the point of view that you can see it. And you should be looking at a modern wet floodplain. Yep. So, modern wet floodplains are obviously going to look a lot different than very ancient wet floodplains, because vegetation has such a major control on floodplain sedimentation in the modern. When we wipe that vegetation out, we're going to get very different processes operating, very different products produced by river overflows onto the floodplain, which of course is the main supplier of sediment to the floodplain. So, I was lucky. I was lucky in that we stumbled upon a drill hole through Sibley Group. Sibley Group is 1.4 jillion years old, that is 1,400 million, and it's north of Lake Superior in Canada. Lake Superior, of course, is in the middle of North America. It's an extensive unit. It's about 1 kilometer thick, and the units that we're going to look at are the Healy Formation. It has a playa system that's semi-arid underneath, and the climate changes, and it goes more humid, in fact, quite a bit more humid. We get deltaic progradation out into a water body, which we don't know if it's a lake or the ocean, but it's a big delta system. It's 200 meters thick. And on the delta top, we have a fluvial system. And it's that fluvial system that we're going to look at in core. So this is a core study. Even though this is 1,400,000,000 year old rocks, they're non-metamorphosed. They're basically quite almost flat-lying in most places, and they're just great things to work on. They're consolidated enough that there was great drill recovery, and they're not messed up. So this is just a log through it. Each one of these sections is about 20 meters, and one stacks on the other. The bottom is the bottom left. The top is the top right. And in slightly shaded are the channel sands. And as you can see that there's some thinner channel sands here, and there's one thick channel sand that goes all the ways here. It's about, what, 40 meters thick. Big channel. But you can also see that there's lots of off-channel deposits. There's lots of floodplain deposits that are quite thick. They're not just filled in mud and fine sand in abandoned channels. They're real floodplain material. If we look at the core, this is the top of that main big channel, and near the top it starts getting the floodplain. You see the floodplain is dominated. It's obviously mottled and bioturbated vegetation. Obviously. When we take a look at it, what we'll see are basically sandy, rippled, muddy sand floodplain deposits produced by overbank flow, and sandy units that are sharp-sided, 5 centimeters to 1.5 meters thick, that were produced by crevasse splay breaking of the levee. So we know there were levees because we're getting crevasse splays, and we'll get back to the levee problem a bit later. Now, if we look at the typical laminated floodplain sediments, we'll see that we find a lot of ripple lamination. It's mostly fine sand. muddy fine sand in places, lots of clay drapes on it, a lot of ripple lamination. There's more ripple lamination, black clay drape, black organics. So we see organics, but all they are is really a black stain in the more clay-rich units. And little rip-ups of, where did my thing go? There it is, little rip-ups of organic material. Now, what we're just looking at is what we call lensy bedding, because it's lensy, but we also get what we call wispy bedding. Wispy bedding is when the lensy bedding gets more soft sediment deformed. And soft sediment deformation is prolific in these deposits. The lensy bedding itself is slightly deformed, as you can see, is slightly messy, but it gets a lot messier in a lot of places. So the main lithologies on the floodplain are these lensy bedding and wispy bedding caused by ripple migration and loading into the soggy floodplain. And that's how we know it's wet, because of all this soft sediment deformation. It's speaking to a very, very wet environment. And in this section, messy. We can see the nice into the silt. Again, mostly fine sand to, in some places, a little bit of medium sand, mostly fine sand, very fine sand, and clay silt. Drapes going through the thing with mud cracks. So we're getting some mud cracks. There's a little mud crack there. But we don't get a lot of mud cracks, showing that we're not getting intense drying events. And the units that have mud cracks will tend to have a fair number of them. So there seems like there were higher areas that were able to dry out enough so that we could get deeper penetration of mud cracks up to a couple centimeters. But for the most part, everything was low enough that the groundwater table was close to the surface, and though the surface would dry, as we'll see evidence for in a few seconds, the mud cracks wouldn't really propagate down into it very far. And there's just some cross sections of mud cracks. They're filled with little pits, little soil pits. So calling them soil is a real stretch, because they're basically dried out mud and silt pieces that were washed into the mud cracks by flow across the floodplain. So the mud cracks aren't filled really by the sand coming out of the main channel during overflow events. They're filled mostly by rainfall events washing dried out mud flakes into the cracks on the floodplain. We also get nice layering in places, but with lots of these mud rip-ups. So there's mud rip-ups all through it, just little mud flakes all through the thing. In thin section, they look like this. They're dark because of high organic content. And again, this is showing that the surface is drying, but it's not drying deeply to get crack development. Only in a few places do we see that. For the most part, it's just a little surface area drying. And we also get erosion. Of course, these are all thin sections, as you obviously know. And erosion, nice erosion here. But again, nice little microalluvial fans building off this eroded side of a silty unit. Again, showing little flows going across the floodplain, depositing this one, then some more silt was deposited, it was eroded, and we got another flow depositing this little avalanche surface. This is a big advertisement for having a good look under your microscope, using thin sections, at your fine-grained units. There's all sorts of neat stuff in these fine-grained units when you see them. However, as you all know, in most of these non-vegetated systems, fine-grained units are few and far between. We also get ponds, small lakes, where the layering is nicely preserved. It's not all loaded, though we do see load structures in these as well. And we also get nice ripple laminated sands in these ponds when we get inflow during a crevasse splay event. When the crevasse splay goes into the pond, it tends to ripple laminate. And the tops of these will have nice current laminate. Let's try that one again. Nice wave ripples. These are obviously current ripples. Tops have wave ripples as they get reworked by wave activity. And then you can see the general wispy nature of the normal floodplain here. So, what do we have? Well, we've got crevasse splays coming off the channel. The crevasse splays get a bit weathered on the top. They develop paleosalts, but very, very poor paleosalts that really don't show much chemical movement at all. We've done the chemistry on these, and there's a little bit of leaching of the sodium. There's a little bit of enrichment of calcium, and that's about it. They're very, very poorly developed soils. In fact, I wouldn't even call them soils. They're so poorly developed. And that's the only evidence we have for weathering of the sediments. Then, as these, where these crevasse clays go into ponds, we get ripple laminated sands developed. Normal pond sediments are the nice parallel laminated mud. So we do have muds. But as Daryl was saying, mud production back then was probably very low. So we don't get that much in the way of mud. But in the ponds, we do get nicely laminated, there it is, nicely laminated muds and graded bedding in places. On the floodplain proper that's subaerial, we get this badly contorted layering, basically, lots of mud chips, and in higher areas, we get mud cracks. So, what's the take-home messages here? Well, we get better preservation of the sediment, obviously, because of no rootlet bioturbation. That's an obvious one. So the sediment isn't all churned up, and it's not all mottled green and red. It's not a mess. The layering is quite nice. However, it's different in that it's really dominated by fine sands, very fine sands that are ripple laminated. Reason for this? Well, one of the reasons might be that, though, there's just less mud in the system. But we've looked at the deltaic system associated with this, and there's quite a bit of mud in the delta, though not as much in a normal modern-day muddy system, so there is less mud. But what else is happening here is without vegetation, there's no baffling. There's no vegetation sticking up to slow the current down when it goes overbank. So when an overbank flow, when it goes across the levee, there's no vegetation on the levee. The flow doesn't decelerate. In fact, the flow may accelerate a little bit going down the back of the levee. Would there be levees? If there's little vegetation, when the flow goes into overbank status, over the bank, there's no vegetation there, it's not going to drastically slow down, which is one of the main things that forms levees in today's systems. However, the flow does spread out, which means you get more bed friction. Friction with the bottom will cause it to slow down, so you do have the physics that will build levees, but they shouldn't be as big and as high as modern day systems. They should be much more subdued, therefore much more flooding of the floodplain. So, lack of vegetation, lack of frictional drag, you get better flow out onto the floodplain, it carries the sand out much farther, and you get lots of ripples. During drying, you get the surface dry. Now the surface is going to be a little bit muddy because that's the last stuff that settled from the last flood event. It will dry out, and also there's no shade. Without vegetation, there's no shade, and this is another big factor. Without shade, the sun is beating down on that floodplain all the time. The surface will dry fairly quickly, and so you get lots and lots of little mud chips that are going to be reactivated and moved around during a rainfall event that the stream might not even go into flood. The rainfall event will still cause water flowage across the floodplain and wash those little mud chips around. And of course, when the stream does go into flood, they'll wash around even more. You get desiccation cracks locally, and they're filled with very localized material from the floodplain itself. These little soil, no, I shouldn't call them soil, little mud flakes that were baked during the sunny days, as our Prime Minister likes to say, sunny days. Anyways, were baked during the sunny days and are moved around during any rainfall event, and then they accumulate in the little cracks. Soft sediment deformation is all over the place. It's just ubiquitous, and that's because groundwater table at or near surface, everything's wet, you get sand delivery, it sinks in. Lots and lots of loading, huge amounts of loading. That's what struck me when I first saw this core. It's just loaded. It's just a mess with loading. So it's not a mess with bioturbation, it gets to be a mess with loading. And immature soil development, probably without roots, there's the main cause of soil development is removed, and they're very, very immature. I wouldn't even call them soils, and they're very, very localized just on the tops, really, of the crevasse plates, which were a little bit higher above the floodplain. These crevasse plate fans, and so they get a little bit weathered, but not much at all. And that's the end.
Thank you so much, Phil, for these slides. It's a fantastic compilation of really interesting deposits. We've got a number of questions. First one from Shirley McMahon, who's asking, how can you be certain from cores that fine-grained units are overbank deposits and not lacustrine sediments?
Oh, okay. Because we do have lacustrine sediments, and they look quite different. On the slide that's still up, section B is lacustrine. It's nice, it doesn't load, and it doesn't load because the sand in the lacustrine system is being supported by the density of the water. So the sand only has a density of 1.6. It's not heavy enough to load. It loads much easier in a terrestrial environment where it's not supported by water, and once the ripple there, the water goes away, the sand loads into the muddy substrate, and that's at least my reasoning of why we don't see this prolific loading of the sand in the lacustrine stuff. So we've got stuff that we're pretty sure is lacustrine, and then we've got stuff that looks really different. And also, we have these channelized sands that cut through this stuff. And to put the channels through the lake system would be sort of difficult, so it makes a lot more sense that it's the floodplain material by the side of the lake system. Also, we've got the delta underneath that we've worked on, and we know where the distributary mold bars are, where the shoreline is, and we know that we're basically above the shoreline deposits. So it makes sense that these are floodplain. But in one of the other holes that we'll be publishing on this coming year, we do have a big lacustrine system developed. Actually, we have a couple of lacustrine systems that are either lacustrine or interdistributary bays. You can't tell the difference without vegetation. And it, again, it looks very different than these loaded ripples that are all through our floodplain. Okay?
All right. Thank you. Thank you. In the interest of time, we'll probably just move on and make Renato Almeida the next speaker, who is talking to us all the way from Brazil.
Hello? Can you
Yes.
see me? Great.
Not yet.
No? And what about now?
Yes.
Great. So thank you very much. I'm talking from São Paulo, Brazil. We had some, let's see, 15 people in the room here. And just one of them can actually answer your polls. So we are working as a collective here. I will try to, can you see my screen back there? Okay, can you see it?
Yes, we can see the screen. It's maximized. It's good.
Great. So let's start. Today we want to discuss with you a little bit of the spatial variability in the depositional architecture of some of the pre-vegetation systems we have been working with here in Brazil. And the main point is that most of this incredible diversity of architectural elements that Professor Long has showed us, and of course the nowadays clearly visible large amount of floodplain deposits that Professor Freilich has just shown, we just want to put those things into a broader context and try to understand what controls the variation in area at the basin scale of those things. So we want to discuss the work that has been done in different projects, individual projects, mostly by André Marconato in his PhD and Bruno Turra in another project, supervised by me with the help of Bernardo Freitas. So we just wanted to think in terms of this larger scale spatial variability, what would be the implications of some things we do know about the different behavior of fluvial systems, and one of them is known since the 70s, which is that the lack of bank stabilizing vegetation causes those fluvial channels to be much wider and therefore shallower for the same discharge, and that would have strong effects on the transport efficiency regarding sediments. Of course, that would result in different patterns of grain size segregation along stream. In the same direction, floodplain processes, of course, would be quite different, and the reduced roughness on floodplain surfaces would lead to increased water discharge and sediment input, just like we saw in the talk just before me. And of course, that would imply in different sedimentation rates and would also influence strongly the transport efficiency inside the channels, because a much larger proportion of the water discharge would be running on the floodplains than what we would get in modern systems. So less water in the channels, more water running through the floodplains. And we wanted to evaluate what would be the consequences of that and how we can test those hypotheses looking at some well-exposed pre-vegetation fluvial systems here in Brazil. Okay, most of the ideas were initially put to test using simple 2D models of sedimentary transport dependent on the long profile slope variation. And what we can see is that that's a work that has been published in geology this year. And what we can see that in pre-vegetation systems, because you have lower efficiency of transport inside the channels, you would then end up with a much greater proportion of high slope systems than in modern day ones. So that's this light pink here is the highest slopes on the profile, preserved as sediments. And that could explain why we have such a large amount of high flow number structures and shallow channels on those systems when comparing to modern day ones. But of course, there are other differences that we wanted to test. And in order to try to recognize what's the actual variability, both along stream and across in a transverse direction to the channel, we studied 3 different successions here, one of Mesoproterozoic age, one of very late Neoproterozoic, and another of early Cambrian age. And all those 3 are just gently deformed, not really metamorphosed. And of course, we can't go into much detail regarding sedimentary structures and detailed interpretation, so we are talking in broad terms just about main channel successions, minor shallow channels, and floodplain deposits, and try to understand how that varies both along stream and laterally. At the basin scale, we did a lot of mapping and paleocurrent measurements and vectorial measurements of bounding surfaces as well. So the Tombador Formation is in northeast Brazil here. It's very well exposed, good place to visit. And we have different types of channel belt successions. Some of them are sandy and with lots of cross-stratified sandstone organized in inclined cossets that might have been bars inside these large fluvial systems. At some parts of the system, there are lots of coarser grained fluvial bars, conglomerate bars. At other parts, channels go much wider and shallower. That's what we call the minor channels. And in most of the succession, what we find is those laterally extensive cross-stratified sandstone, which are typical of the classical sheet-braided model. Locally, we can find some things we interpret as floodplains as well. Those are rich in silty sand with exposure feature, mud cracks, raindrops, and lots of ripples, just like what we saw right now. And at the map scale, at the tail map, what we can see is that close to the margin, here the paleocurrent is to the west, and we are looking at the eastern margin of the Tombador exposures. And at this area, we have a pretty good amount of conglomerates in between the sandstone. We did some measurements in different, with Bruno tool in different sections. And at the logs, we can see that conglomerate beds have some considerable thickness, but they are not correlatable across more than just a few hundreds of meters. And those are intercalated in between the sandy successions, with some of them with large prostrata, and related to a lot of aeolian deposits. That's pretty common in the Tombador Formation, aeolian dune deposits. In a map view, what we see is that at the eastern border, we have more conglomerates and a lot of diamond occurrences, which have been explored. And at the same stratigraphic levels, just 25 kilometers away from that in the current direction, very few conglomerates and no diamonds. So the finding downstream was really rapid for this system. And of course, it looks like the channels were deeper here and shallower there, because we have lots of very thin and wide sandstone bodies at the distal parts of the system. But what would be those shallower and more frequent channels? We can have a hint on what's that, looking at another succession exposing different parts of a silicular system in the early Cambrian of southern Brazil, the Varginha Formation. And here we have the main channel belt, mostly comprising throw and tabular cross strata organized in inclined cosets. That would be bars inside the main channel belt, and that's mostly axial to the basin orientation. But at some parts, other parts of the system, we have these beautifully exposed finding upward cycles with erosional bases and ending up with cracked muds that can easily be interpreted as events of flooding and abandonment and exposure that would be shallow ephemeral channels. But those two successions are coeval and especially related to sandy floodplains, silty sandy floodplains, intercalated with those ephemeral channels. So what we see here is that most of the shallow channels are actually channels flowing on the floodplains that would be responsible for the most part of that discharge partition without the common roughness we got today on modern day floodplains. So in our reconstruction, we'll get something like this: a main trunk river, some perennial rivers flowing as tributaries, and lots of ephemeral fluvial channels flowing through the floodplains related to aeolian dunes rework in those sediments. Of course, it's an extensional basin with a well-defined base-border fault. If you look at possible modern-day analogs, you see that when you have major floods on unvegetated plains, you get these complex networks of shallow channels, both in glacial outwashes and dry environments today. We really think that most of what we think is sheet-braided channels could be something like that. Ephemeral because they are on the floodplains, which are by definition ephemeral regarding flow. But on those two successions we studied, we can clearly recognize that there is at least one perennial channel at some part of the basin which is coeval to those minor channel systems. And now having a look at the last successions we want to show you today. It's in the same basin as the Varginha Formation, but it's a little bit older. It's late New Proterozoic. It's called the Santa Barbara Group. Again, deposited inside an extensional basin with normal faults bounding it. And we see, in general terms, the same three facies associations, channel belt successions with lots of cross strata organized in in inclined cossets, those are dominantly cross-strata. And events of rapid floods with finding upward successions ending up in cracked muds with lots of high flood number structures related to sandy, muddy floodplains with mud cracks and some events of sand input with lots of ripples and some larger bed forms. When we look at these last successions, the Santa Barbara group, it's very clear for us that the floodplains with minor channels are coeval with the main trunk river with deeper flow for at least 300 meters. So it's like
2 minutes.
Okay, the floodplains are vertically stacking just side by side with the main channel. And as a conclusion, that's something and the alluvial fan systems are spreading over those floodplains, and the floodplains are positioned just on the top of the main depot center. That's actually something we would expect from how Precambrian or pre-vegetation floodplains behave, because given their increased sediment input and water flow, the lateral, the transverse slope between the alluvial ridge and the floodplains would be much reduced, and that would inhibit a lot the very frequent avulsion. So the channel belt would be more or less fixed because the degradation rates on the floodplains are much greater. So as a conclusion, what we think is that difference mostly on floodplains, but also in stabilized banks by the main channels, would have a very strong effect on the long stream variability and the lateral variability as well, because they would control the efficiency of sedimentary transport. Those systems would have a very increase. It would be much more difficult for those systems to bypass sand to distal areas. But on the other hand, given that they would have a much larger discharge both on floodplains, it's very easy to see that they would preserve much less mud. And we can see here in Brazil, we have lots of pelites of Proterozoic age metamorphosed in several successions, and they are all marine. So we are not pretty sure that we had less mud, but we think that the mud was bypassing the fluvial systems and reaching the ocean, while most of the sand was being stacked on fluvial systems. And the floodplains that would behave mostly as a complex network of shallow channels with much greater sedimentation rates would hamper the main channels of having frequent avulsion. So we think that the channels might have been much more mobile than today, but the channel belts could have been more fixed than in modern day examples. So when you are trying to predict what would be the variation of environments in a pre-vegetation or alluvial plain, you should consider that they could be much more vertical fastest transitions than what we get today. Thank you. That's it. Ariel, are you there?
All right. We have questions here. Can you hear me?
Yeah, I can hear you. Can you hear me? No,
yeah.
I'm afraid that you...
I'm afraid. It's all worked very well. We don't have... Do we have questions, Arnold? I can't see them now. We do. We have one question that is related to the relative size of the floodplain channels and the main channel. Can you say something about the dimensions of them?
We can only think in terms of relative depth, because the width of those preserved sand bodies, they might have been altered because there is a lot of lateral shifts and erosion and lateral preservation. So what we can tell is that the main channels most of the times are 10 times thicker than the minor ones, at least.
Okay. There is another question which is also posed to Phil Freilich, which you might want to comment on. Do you see much heterolithic deposition on the floodplains and in your floodplain deposits? And how do you interpret that?
We have things that are really similar to what Freilich showed us. Lots of tiny mud chips and sandy silt, and we don't have real continuous mud drapes and sand drapes. It's just you have both lithologies, but you don't have those clear heterolithic horizontal strata. No, we don't see that.
Phil, would you care to comment on that particular heterolithic character of deposits?
As was just said, it's heterolithic in one aspect, in that the mud is there and the sand is there, but because there's a lot of erosion, probably driven by drying due to lack of shade and that sort of thing. It's very laterally discontinuous over millimeters to centimeters. So we have nice mud drapes, but they are wispy. They get cut off by the next ripple erosion little pit, and so it doesn't really look heterolithic, even though technically it is, because it's two different grain sizes. But it's not heterolithic as in you'd think of normal heterolithic bedding, say a point bar or something like that. It's much more laterally discontinuous on a very small scale. But I just wanted to mention something about just mentioned in the last talk about the channel thicknesses. That's what we see. We've got one major channel in our core that's about 40 meters thick maximum. And then our other channels, it's always weird because our other channels are about 4 or 5 meters thick. So we're getting the same sort of 10-to-1 thickness ratio as was just mentioned for the Brazilian example, which is sort of interesting.
Okay, thank you very much. I think we'll leave it here for now. We'll try to answer some more of the questions a bit later on. We are going to have a break. Which means that I will make myself presenter, share my screen, but the webcams and microphones will be off. We are reconvening at 1:15, so right here in the UK right now it's about 6:40, so at 7:15 in the UK, which is a rather different time for many people that are all over all over the world. So in 35 minutes we will start again. So I hope to see you then.
bar deposits have been described from the Torridonian group. There is this overall abundance of preserved meandering channel planforms on Mars, with no conclusive examples of braided planforms. So we need to understand non-vegetated systems through modern terrestrial analogs. So we need more modern terrestrial analogs. We need to find examples on active sedimentary basins, which are those sediments likely to get preserved in the rock record. We need to identify and characterize those examples of modern meandering fluvial systems with no vegetation, and provide fluvial morphometric parameters with which to understand their particular dynamics and characteristics. And how we're going to do that is using Google Earth and Landsat imagery to scan modern continental sedimentary basins developed under arid climate. We need to set the tectonic settings, basin settings, climatic settings, river flow regime, and use GIS facilities to extract river sinuosity, gradients, discharges, meander belt width, and channel width. So we use this map of a climate world map and map with the modern sedimentary basins to cross up this information to get modern rivers on desert basins. We got river discharges databases from various sources, and presenting now the meandering rivers in modern desert basins. We have a large number of meandering rivers on modern desert basins. Here's a map with examples on all continents, but Antarctica and Europe for obvious reasons. Here's the example of the Senegal River and the Sahara. It's an exorheic intercatonic basin. It's a multi-channel system with a relatively flashy discharge, sinuosities of up 1.6. We can see floodplain lakes. We can see here the main channel and various ana branches, and we can see the lateral erosion of some ana branches on laterally eroding aeolian dunes, and with the preservation of scrolls. In an ephemeral system in the Sahara, in the shot, we have this endorheic intercatonic basin, also a hot arid climate, and again various paleo channels preserved with scroll preservation as well. The inner Niger Delta, also in the Sahara, with a not so flashy discharge and same climate, multi-channel system, but with sinuous ana branches. Even when they are laterally contained by dunes, they still develop these wandering to sinuous patterns. We have the Lake Eyre in Australia, which is an intercatonic basin, an endorheic basin. We have multiple channels with wandering to meandering planforms, scroll preservations. We can see here cutoffs, crevasses place. Now in cold arid climate in the Tarim Basin in China, we have this ephemeral system here, which is presented in various examples of preserved paleo channels. We can see here they're all characterized by highly sinuous single channels. In the Kazakhstan, in the Karakum Desert, it's an endorheic intercatonic basin. We have beautiful examples of scroll preservation. We have oxbow lakes preservation, and there is no vegetation at all in this system. Here a more detailed analysis, a more detailed image of this with oxbow preservation. We can see that the lateral erosion of floodplains and non-vegetated floodplains. So will these point bars be preserved as laterally continuous sand sheets? How will they get preserved? We don't know. So we need to get our feet there on the ground to see how they're preserving. An example which we can relate to the rock record is the Deseado River in Argentina, which can be related to the Altnabis member of the Applecross Formation. There's a paper on Precambrian research, and there are some examples of mud crack preservation, crevasses place. There's these examples of point bars, and this is we believe that what is providing cohesion to this system are these mud-prone systems. So the banks are being stabilized solely by the presence of fine-grained sediments. We can see here that floodplains are not vegetation at all. So we have contrasting channel width and meander belt width, a whole gamma of different stream gradients and sinuosities, with channels varying from up to 1 kilometer's width and even very smaller ones. Gradients can vary from more than 200 centimeters per kilometer to less than 1 centimeter per kilometer. We have contrasting basin settings, yet we have all this, the development of meandering platforms. We have this multiple channel of the Senegal River here. It's an exorheic basin, and we have here in the Tarim Basin an endorheic basin. We have contrasting river discharges, yet the development of meandering systems, or some of these are more like wandering, but these are meandering systems. And here in the Senegal, we can see that vegetation is following the appropriate environment. It's not inducing the environment to do so. So we can see that by this lateral erosion of non-vegetated aeolian dunes. We have also contrasting stream gradients from more than 200 centimeters per kilometer and less than 1 centimeters per kilometer. Contrasting river flow regimes as well, with perennial and ephemeral, yet all those are meandering. Even if we compare with contrasting vegetation covering, there is an example on the left side of Kazakhstan Uzboy Channel. And to the right side, we have the Taquari River on the wetlands of the Pantanal Basin. They have similar sinuosity, similar channel width, and similar meander belt width. So, to conclude that, meandering channel systems are common geomorphic features in modern desert basins. These systems developed with sparse to no vegetation on channel margins and floodplains. Vegetation, where it does occur, is too sparse to significantly impact the floodplain. They developed in a range of different climatic and basin settings, despite aeolian winnowing, varying stream gradients, and distinct discharge variations, showing that this is a multivariable problem. Channel banks can be stabilized by controls other than vegetation, so as to adopt a sinuous platform. Anastomosed channels can form in the absence of vegetation and with sinuous anabranches, even when laterally limited by longitudinal aeolian dunes. We suggest that meandering channels and straight to sinuous multi-channel systems were arguably far more abundant than previously envisaged by pre-vegetation systems, for models for the pre-vegetation rock record, and fascist models for pre-vegetation fluvial systems, and on the impacts of land plants over sedimentary processes need reviewing, and we need to get our feet on the ground to understand how the geometry and fascist assemblages are on these systems. Thank you.
That was a very good overview. Thank you very much. And I noticed you were going quite fast to make up for some of the time. But let's just take a little bit of time to actually answer a question, because we've got some really good questions that have been posed here. So Shirley McMahon mentioned that the Senegal River and the inner Niger Delta and Lake Erie and Tarim Basin all have a lot of vegetation along the satellite images, or along the rivers, or another way to phrase this, is it possible that you actually need only a very minimal amount of vegetation to affect the rivers, especially those palimpsested by recent aridification from previously vegetated conditions? So how do you view those things?
Yes, my point of view is that the vegetation is following. If you see those images of the Senegal River, you can see that vegetation is following active channels. So there is much more vegetation is much more abundant in the main channel, and the main fact I would say that floodplains are not vegetated. So some of the discussions we've got until now are what are the characteristics of non-vegetated floodplains, and what the runoff controlling the flashy discharge supposedly dominant in pre-vegetation fluvial systems. So I would say that vegetation is following that, and they're not really having a big impact on those systems. They obviously have a much more pronounced impact on wetter climates. These are not certainly not these analogs cannot be used by all pre-vegetation, because of course we're not dealing with any humid climates. So I guess that's it.
Okay, thank you very much. We will switch over to the next speaker. Alessandro Irpi is going to present to us from Canada.
Hello, Ivan. Can you hear me?
Yes, I can hear you.
And I'm showing my screen, so give me the green light when you see the screen, please.
I see the screen. I'll send you a webcam request as well.
I'm here. Hello, everybody. Okay, so I'm starting. I would like to take this opportunity to go over some of the results of my postdoc. This is a talk about collaboration with colleagues from the Geological Survey of Canada, University of Padua, and Utrecht University. Let's start from the state of the art. We know from the early work of Sham and Cotter that in the absence of vegetation, the discharge patterns and the channel morphology would have been different. And more recent work by Davis and Gibling actually provided a nice chart that shows us how the evolution of fluvial style in the Paleozoic was influenced deeply by the evolution of vegetation itself. What I would like to point to here is that, however, we still have a lack of a proper compilation of channel morphometry for pre-vegetation rivers. In other words, most of what we know about pre-vegetation rivers derives from the comparison of their sedimentary record with facies models that were developed from modern rivers. And without knowing exactly the size and the extent of pre-vegetation sand bodies related to fluvial processes, we cannot really understand how the river itself, the rivers themselves were behaving. So trying to address this problem, we adopted an approach heavily dependent on remote sensing and based on very large exposures of fluvial rocks where channel bodies, no matter how big, it was possible to appreciate their full extent. So you can see in this image here in the bottom that the selected database derives from a rift basin in Scotland, 1.2 GA, two sag basins, two intercatonic sag basins in the Canadian Shield in green and yellow, and a foreland basin, the oldest in the dataset. So the database spans from 1.9 to 1.0 GA and is representative of both proximal and distal drainage, although, as I'll point out in the next slides, there is a bias towards proximal. I'm not going to spend too much time on the full sedimentological details of each of these formations. I'm just going to skim through them, and there is literature already out there for those who are interested. Starting with the 1.9 GA Burnside River Formation, we're in Kilohigok Basin. It's a foreland related to the Thylon origin. 52 very large channels with generally narrow profiles were observed. When I'm saying very large, I mean that the channels were anywhere from several hundred to a few kilometers wide. And in some cases, they were deep up to 20-25 meters. There was a lot of basement topography observed in the nearby of the outcrops. And this is something that contrasts with the second case study that we observed, the 1.6 GA LS formation in the basin. This is accumulated in an intertectonic sac basin. Only 8 channels were observed. They were prevalently broad and preserved both nearby and away from basement topography. The third case study is the 1.2 GA store group. It's the oldest part of the Torridonian. It's a rift basin, but despite this, bears strong resemblance to the Burnside River Formation in that both narrow and broad channels were observed in the surroundings of, they were engulfed within valleys characterized by steep basement topography on their side. And in this case, a number of 84 channels were observed. These that I've listed so far, they were all related to active stages of channel filling. The fourth example is the Nelson Head Formation of Broken Lyre. Daryl mentioned this formation already in his keynote. We had the chance to visit the outcrop again in 2014, and we were also lucky enough to manage to get good coverage of the main cliffs and map the lateral extent and thickness of 12 channels that were filled with abandonment, silt, and fine-grained sand. Here's a slide that briefly summarizes the entire data set. So we have something that spans from 60 kilometers to up to 3,000 kilometers from the original headwaters in the current paleogeographic reconstructions. We have different styles of clustering, although it seems that proximal channels are much more prone to show clustering. And we have a relatively high distribution of sizes, pointing to a significant geomorphic variability, although with relatively low inferred sinuosity in all of the examples that we considered. One question that I would ask myself would be, how can you tell that these are channel bodies and not valley fills? And this is critical, and we adopted 3 criteria. So first of all, the channel scours are not part of widely traceable erosional surfaces, and they could never be followed or traced along interflows from one channel to another channel. More in general, channels were in most cases stacked vertically and almost never horizontally. Channel bodies are actually contained within much larger erosional surfaces that were interpreted as the actual floor of incised valleys. And the third criteria, channel bodies are not substantially bigger than the nested erosional surfaces that are observed within them, and possibly related to bioaccretion and reactivation. Once restored to the local paliflow, this entire database of 156 channels was plotted in a logarithmic space of width versus thickness. And we can observe a fairly linear correlation within the database. We can observe that most of the data points fall within a width-thickness ratio of 10 to 100, with highest frequency around the 40-60 interval. Now, this is striking because when compared to both post-vegetation and modern channel morphometries, we can actually observe that the overlap is quite significant. So the study dataset was compared with 29 rock units compiled from literature that exposed fully preserved channel bodies, both active and abandonment interval, and with a compilation of 192 perennial cross-sections from perennial alluvial rivers not modified by anthropic activity. So in other words, one of the conclusions, the main conclusions that we can reach is that while most of the debate in the past years was focused on whether pre-vegetation rivers are exclusively braided or also sinuous, another thing to consider is that the morphometry of the channels themselves, independently from their plan view style, seems to have been fairly constant in at least the last 2 billion years. And this is a conclusion that we reach thanks to extensive remote sensing on large exposures. So, of course, there will be a bias heavily dependent on where these exposures are available, but nonetheless, the morphometry seems, at least for large perennial fluvial systems, seems to have been fairly stable in the analyzed time span. And this is all. I would like to acknowledge contributions from Geological Survey of Canada and NSERC, most of all, and I'm open to questions.
Thank you very much. First, I have to apologize. I'm trying to upload some of Alessandro's papers, but it seems to have been a little bit tricky to actually get them off the handouts. I've relabeled them and will upload them shortly, as fast as I can, because I'll be presenting next. Are there any questions?
Well, I do. Can you hear me?
Yes.
This is Mauricio, right?
Yep.
Yes,
Alessandro, are you or can we derive this approach of remote sensing approach to outcrops? Can we develop outcrop techniques with which to study less, not so well exposed successions?
Eventually, at the end of the game, it all revolves around the fact that you have to observe what you interpret as a fluvial channel body in its entirety. In a way or another, you can do this with remote sensing. In some cases, actually, in most cases, you cannot tell from the ground that you are within a channel body, and you will be able to see it only from satellite. I know that in other cases, GPR, the ground penetrating radar, is showing increasingly a high potential for picturing sand bodies that are not outcropping in their entirety. But the only thing that I can say now is, in a way or another, you need to see the entire channel. Like, we cannot apply models of deposition that are based on shallow, broad channels unless we actually know what the geometry of this channel actually was.
Okay. Aaron?
Yeah, thank you very much. I uploaded a few papers. I will upload one more, and then I'll move on to presenting. There we go. Presenter. There we go. Show my screen.
I actually have a chat from Daryl, but maybe it's a question that he wants to ask in private. I'm not even entirely sure it's for me or to another presenter. Arya, you can go ahead.
we can cover these things a little bit later if we've got a little bit of time left, and and there will be recordings, and there will be I'm sure a lot of a Twitter chat and email chat, and any questions that we are missing, you can always come over to the Fluvial Conference in Calgary, which is a fantastic opportunity for everyone to meet again. Can everyone see the presentation?
I'm seeing it.
Okay.
I'm seeing the schedule, actually.
Right. We go to page number 2. It's the start of my presentation. I had the schedule as the start and then the start as the start. Right. So my presentation is on channel and floodplain dynamics in the Cambrian, Illinois basin. So interpreting rocks from the Cambrian, Illinois basin. The reason we are doing that is that we are pumping CO2 into these rocks, and we want to understand what is going on. In order to do that, we are combining a few things. So we need a good conceptual model of what the rocks are made of, and all sorts of metrics that we use in order to come up with these conceptual models are also of value on their own as a statistical characterization of the rocks. We build that into 3D geocellular models, and we use all of that to answer some of the questions about CO2 plume movement, pressure fronts, microseismicity, and so on. And that's the rationale for looking at these kinds of rocks. So within the rocks that we are studying, and it is all relatively nicely sorted sandstone, it's all sandstone, we've got a beautiful river channel. And so this is a pre-vegetation river channel in the Cambrian. The channel deposit has a coarse base. It's roughly composed of 5 distinct large-scale units, of which 3 are distinctly fining upward. It's mostly composed of dune sets and some ripple sets. There's no distinct vertical thinning of sets, as you might expect, with the biggest dunes being at the base and thinner dunes being at the top. But we do have 2 angle of repose bars on top higher up, rather thick sets. I'll talk about those in a minute. This channel deposit is overlying some marine and coastal deposits that are below it, which include foreshore deposits that are also cross-stratified. And it's overlain by aeolian dune deposits and lots of planar strata. Now, the rose diagrams at the base will give you a nice idea of how well behaved our river channel is relative to the shallow marine and the aeolian deposits, and also the nature of the cross strata is quite different. So we can pry them apart and we can study our river channel in detail. Obviously, the reason to focus on the river channel is that it is considered to be a very important artery through which sediment is routed through the landscape. So when we're trying to figure out what's going on with this river channel, we want to do some quantitative analyses, and so we're looking at the individual dune sets. We have 41 dune sets with a mean of 5 centimeters. And we can use the Paola and Borgman and Leclerc and Bridge models to sort of interpret that, and it gives us a formative dune height of about 12 to 21 centimeters, which is a reasonable sort of medium to small river, about South Saskatchewan sized. We have 2 bar deposits indicated, bar 1 and bar 2, and with little black brackets. Their thicknesses are 43 and 48 centimeters, and bars themselves are also a useful indicator of formative flow depths. In addition to that, those bar deposits are angle of repose cross-stratified sets. They're thick sets. They have pre-sorted cross strata in them, and those pre-sorting patterns are generated by superimposed bed forms and can be used to interpret the volume of the superimposed bed forms. And that indicates, if you use a sort of a fixed height-length ratio of about 0.1, it indicates that they were about 8 to 16 centimeters in height, the superimposed dunes. So all of that sums up to sort of 3 metrics that you can use as a sort of a multi-proxy way of looking at sort of formative channel depths. and they all match up quite nicely. What they give us together, the dunes and the bar sets, that the channel depths were over ½ meter deep and more likely in the order of 2 to 3 meters. However, the total channel deposit was 6 meters, which means that we have a multi-story deposit, or we have a channel that has been in the same location for a long term during aggradation. Now, what we want to know, in addition to the behavior of that channel, the thickness of that channel, is what else is going around there and what are these channels placed in. So we're looking at floodplains here. And we've got a large amount, up to about 30% of the core, that is composed of these sort of planar, crinkly strata. These are composed of mostly sort of fine to medium sand. They have got some granule layers in there, and they've got these weird, dark, crinkly layers in there that stand out quite nicely when it's bleached. And what these are is they are small, thin veneers of enrichment by clay. And the way we interpret these is quite crucial. But what we have in an association with these is that we've got a variety of wind ripples and granule layers. We have some pseudo cross stratification, and occasionally we have some areas where it looks as if they are there are burrows or gas escape structures. The interpretation of these crinkly layers is that we have traces of biofilms. They were probably wet and likely sticky surfaces because we have lots of adhesion structures, adhesion warts and adhesion ripples. And so both of those indicate that there is a wet environment. We expect biofilms to form in wet environments, not in very dry environments. And yet we do have a fair amount of aeolian ripples interbedded with them, and coarse sand and granule lags interbedded with them. So what we are looking at here is a wet plain which is dominated by aeolian activity, which seems a bit of a paradox. And it is indeed correct that there is no perfect modern analog that we can think of. So I've put a few examples below of coastal deposits in the Netherlands, of sandur deposits in Iceland, and of beautiful national parks that you could go to in Brazil. If you didn't have a reason to go there, you have one now. But we don't have the perfect analog. What we do know is that groundwater is essential for, it provides the basis for sedimentation. Below the groundwater table is typically where all the sediments are being preserved. And so we know this works for whole basins. This is from Nigel Mountney's publication in 2004, and we know groundwater surface is very, very important for the whole basin deposition. We can do this also at a much smaller scale, thinking about the river as a base level and the floodplain as a sort of a self-organizing plain, where the groundwater level determines whether or not you've got deflation or adhesion, and the sediment balance between deposition and adhesion onto this plane or release from this plane determines whether or not you can build desert dunes. So this comes back to earlier questions as to where do all the aeolian sediments go. We have potentially a solution right there in that.
2 minutes?
Yeah, thank you. Back in the days, there would have been quite a possibility of having wet climates with lots of aeolian activity. This numerical experiment, we can use a couple of simple equations for that and run some models in terms of wetting and drying, or what happens at recharge. And the two controls here are rain, the recharge, and the river, which is the base level, and the rest is more or less self-organizing. Now, there's a number of processes in there, but all of them basically end up being great questions and great implications. So in terms of predicting the paleo surface topography away from the river level incites groundwater surface waves. So because when you change the base level, the groundwater takes quite a while to respond. The rain and conductivity of the plane would have controlled the length and amplitude of the surface wave. So there's quite to generate wave-like structures that of wetting and drying that move across the plane. There is, of course, a buffer against deflation because we have a capillary fringe, and the deposition can take place when the groundwater reaches the surface. And then we've got, in addition to that, granule lags and obviously the cementation by biofilms. Landscape set a really important context for the behavior of the river channel in a larger scale. And so the topography, we know, is a very important control in avulsions, whether or not the channel can shift its course entirely to a new location. And we did observe that there is quite likely a multi-story or a stable channel. So these things seem to match up. So having a floodplain that controls the position of the river. The groundwater level is obviously controlled by the base level or the climate, and by the sea level and the river profile, and then by the climate, by the recharge. So we've got an indicator here of climate as well as sea level change. And so in a pre-vegetation Earth, the aeolian processes would have occurred in all types of climates, would have been prolific, but may not have resulted in the formation of distinct dune fields, aeolian dune fields in that case. So the conclusions are that the Cambrian Illinois rivers were likely surrounded by floodplains that could operate autonomously due to wind, in which groundwater and wind are controlling deflation or the erosion and deposition, and the river itself is not necessarily acting as more than a base level. The riverbanks would have been more erodible, but the autonomous floodplains placed the river channel in a different landscape context, which would have affected the way the river is behaving at a larger scale. And such an aeolian fluvial system is unlike anything that we have today, so we need to look at these detailed processes in order to determine what is going on. I would like to acknowledge the GSCO2 project, and I would like to open the floor for questions.
All right. Any questions? Well, I have one. Could you please elaborate a little on multi-proxy interpretation of crossbed sandstones?
Yes, there we go. So yes, I did expect that there would be a question about that. What you can do when you're looking at cross-bedded sandstones is you can look at the individual sets and their thickness and use established theories to relate those to the formative bed form heights, and then you can relate the bed form heights to the formative flow depths. You can also look at the types of structures you see in bars, and when you have bars with superimposed dunes. The volume of reactivation surface generated by successive dunes, or in the case of relatively small dunes on a relatively large bar, you get pre-sorting in the strata. Those volumes are directly comparable to the superimposed bed forms. And the relative size of the superimposed bed form and the host bed form determines which structure you see. So we've got a couple of metrics that you can use to compare against one another.
Thank you very much, Arnold. I think we're short on time.
Okay.
Link to the next presentation.
There we go. We can see the screen, but you're still muted.
So, hello everyone.
There we go.
So do you want me to play this in the full mode, or is this good enough?
Full mode is nice.
Okay. Okay, I guess I'm your last speaker of the night or day, depending where you are. It's a pleasure to be here. My name is James or Jai Savitsky, And I was asked to talk about the B-quart model and whether it's applicable to a world without vegetation. So I've put the talk together in a way that will provide some insights on whether it's applicable. And of course, since I'm not a person who has a great amount of expertise working in the Precambrian, although my first part of my career I did that, I'll let you decide whether this way of looking at sediment flux predictions is useful to those working in the geological past. So the first slide just shows you I think information that everyone should know. If you don't have it memorized, maybe this is something that you can think about. So there's about 22 gigatons of sediment that can move off the landscape in today's world into the ocean. Most of that is by suspended load, 94% of the 16 gigatons per year, and 6% of that is as bed load. We also have sediment that's moved around today in terms of glaciers. And even in today's world where there's hardly any glaciers, that still comes up at around 4.5 gigatons per year. And I will talk about that also. And the wind is about 1.5 gigatons per year, so not that much, but it's very significant in the places where aeolian processes dominate. Coastal ocean is around 0.5 gigatons per year, and that's a very hard number to figure out. So that's a highly subjective number at best. The dissolved load is much easier to figure out. It's about 4 gigatons per year. So in today's world, we live in a particulate flux world rather than a dissolved flux world. Okay. So the first chapter I'm going to talk to you about is climate and weathering, and then I'm going to move on to the B-quart model, which is a global flux predictor. I'll walk you through that. So I bring up the weathering because, you know, whatever world you're living in and trying to figure out, I'm sure it will be a different climate world than today. In today's world, the temperature component, in the variances in the mean temperature, you know, they're very much following the latitude, so the insolation. There's some impact, of course, by the continental effect and ocean currents and albedo and cloud distributions. But in general, if you looked at the upper diagram here, you will notice that it more or less follows the banding that you would see for latitudes. That's not quite true for precipitation. In this middle panel, you see the mean precipitation it's on a log scale. It's in millimeters per month. And, well, you can see the intertropical convergence zone across the equator and the trade wind deserts of the world. You can also look at and see the distribution is not following the banding very much at all. And in fact, if you looked at the bottom panel on showing the minimum precipitation on any one of these terrestrial pixels, the mean in blue and the red in showing the maximum values, you will notice that there are maximum precip places in almost every latitude, bar the very highest levels of the Arctic and Antarctic environments. So that's something also to know. Even in today's world, precipitation is not as nice in terms of latitudinally controlled as temperature. In terms of soil thickness in millimeters per year, the upper left panel, you can see that there is a great range between hardly any soil to quite thick soils developed. And if you look here, you can see that some of these thick soils can be in the higher latitudes or they can be in the tropical environments. And if I was to pick a physical process that would go closest to that soil thickness, it would be the coefficient of variation in daily discharge. And you can see there's not quite, but almost a one-to-one relationship between this discharge variability and soil thickness. Where you have very high variability, you get your thinnest soils. And, you know, when you look at the two forms of weathering on Earth today, biogeochemical weathering and physical weathering, there is a fair amount of vegetation impacts on the weathering processes themselves, particularly on the biogeochemical weathering. Biogeochemical weathering, excuse me, seems to be really impacted by warm temperatures, aided by bacterial degradation, bioacid formation, and a high level of humidity, both in the soil and in the atmosphere. So I would suspect you have to think about how much this modern day biogeochemical weathering can impact the availability of sediment and whether that would change any of the model predictions that I will talk about later. And finally, and in my overview of sediment fluxes in general, we should all consider, you know, the land cover distribution, at least for today. And in this diagram, you're looking at the terrestrial surface area binned in 5 degrees of latitude. It's in millions of square kilometers. And of course, you can see that we have a northern hemisphere dominance of land surface. And in the southern hemisphere, you will note that we don't have very much temperate or subpolar land surface at all. In general, though, even in today's world, which is considered part of the ice house world of the Quaternary, you will notice that the greatest land surfaces are in the subtropic and tropical regions. You know, they have 55% of the land surface, so in a sense, today's world is really a tropical or subtropical world, which we sometimes forget in that too many of us live up in this temperate regions of the northern hemisphere and think that's the rest of the world, and it's not. So after that overview of you know, impacts on climate and weathering, I'd like to go into a little bit more detail on this B-quart model, how we came about it, and, you know, sort of what its implications are for today and perhaps in the geological past. If you look at this diagram that was published in this now famous 92 paper, you know, John Milliman, he got this great database at the time, and he broke the world up into those with very high mountains, those with mountains between, you know, 1,000 and 3,000 meters of elevation. And he subdivided that into Asia and Oceania, and another one on Americas, Africa, and Europe, and another one on the Arctic. He did this for a wide variety of reasons, and you should read the paper to see why, but he did that. So there's a bit of geography in this family of curves of load, sediment load versus area. And then you'll see there's upland, you know, in the, you know, 500 to 1,000 meters of relief versus lowland, you know, less than 500 meters, and coastal plain, which is less than 100 meters. And if you were to plot them all onto one overlapping diagram, and down here you'll see you get a family of curves. And a few years later, my postdoc, he collapsed this family of curves into a simple typology of sediment load as a function of basin area and relief. And this dominance of basin area and relief on sediment flux is very, very very complicated, and I can't emphasize that enough. Basin area is large basins are integrators. They integrate all sorts of phenomena like what the vegetation is, geology, hydrology. Large basins dampen out discharge variability, no matter where these large basins occur in terms of climate. And they have very large groundwater pools. The small basins are basically hot reactors. They're the opposite. They, reflect local vegetation, much more latitude, and lithologies are typically more dominant in the principal style of rock type. And relief, it controls the sediment dynamics. It provides the potential energy that can be transferred to kinetic energy. It impacts sediment production and landslides. And of course, because of the storage of water in terms of permafrost, ice fields, and snow fields, relief has a big role. It does it today and it will in the past, even if it doesn't translate necessarily to snow or ice. And I throw this diagram for your entertainment because if you look at it, it's basically looking at only one type of river, the tropical rivers. And this can be produced for every climate zone we have, and you would reach almost the same conclusion, whatever the climate zone, that the size of the river basin is really important. If you look up at the Amazon River for tropical rivers, you'll notice that there's an enormous base flow, not quite 100,000 cubic meters per second, but pretty close. And you can see also very high base flow in the Congo. And as the basins get smaller in size, like the Niger and the São Francisco and Brazil, they still have year-round base flows. And that again reflects the size of these rivers. Once you get below a certain river size, you can get the seasonality of the rivers are such that they can run dry. And they can run dry, such as the Volta or the Godavari in India. And many of these smaller rivers, whether they be in the high precipitation belts of the intertropical convergence zone, like in Indonesia, you can see that these rivers still run dry. And so this is something to keep reminding yourself. The size of the river is so important to the discharge dynamics. Till you get down to one of these tiny little rivers, creeks almost, in Hawaii, and there they just reflect the rainfall events. Moving back to the Bogart equation, in 1999 I worked with one of my doctoral students, and we applied Buckingham Pi theorem to the flux problem because we wanted some sort of theoretical underpinning for what the observations that we were seeing were providing us. So we came up with two dimensionless terms. We came up with what could be considered a hydraulic sediment yield in the first part of the equation with these parameters, sediment load, drainage area, gravity, and density of the water. And you can see that it relates to some potential energy, which is relief divided by area to the 1/2. And with that, it gave us a way to move forward, but we were very frustrated that we really didn't have climate into this formulation. And so there was an attempt over the next few years to try to get climate into it in a more overt way. We didn't want, even though we knew that relief and drainage basin area were important, we also thought that the secondary factors of climate should be in the formula in one way or another. And we worked on lapse adjusted temperatures. We came up with formulas to be able to predict them pretty much anywhere in the world. We looked at this dimensionless flux formula, and we introduced, through this coefficient beta, we introduced temperature in a very overt way. And we came up with two little formulas. One was called the ART equation, based on drainage basin area, relief, and temperature, and another one called the Quart formula on discharge, relief, and temperature. And in this science paper that we put out in 2005, one of the things we applied was the ART formula to what could be considered pristine rivers. And we went out of our way to find data on pristine rivers. It's very difficult today because the human footprint is so large that these data sometimes are the very first years of measurement before a dam was put in or before large-scale deforestation went rampant, things like that. So there's hardly any of this data around, and the ART formula gave us some sense that, wow, this very simple approach on sediment flux seems to make sense and to work. And it does capture, because it overtly takes into temperature, it does somehow capture and into a prediction tropical, polar rivers, etc. So the final paper in that sequence was the Savitsky and Milliman 2007 Journal of Geology paper. This one we were really interested in the human flux. And for this talk, and I don't believe you're at all interested in the human side of things, so I'm not going to talk about that. But there were some advances that we made. We didn't like the idea that there was two separate unrelated formulas, this Quart and this ART. And so we tried to combine them into a single equation. We did this through this area to the 3/4, which was in the ART formula, and directly introduced the discharge into it. And this comes from global observations. So then we got this Bogart equation, where this B part of this Bogart equation relates to these other tertiary factors, such as lithology in the rock types that's being weathered, or the amount of glaciers in your hinterland, or for instance, if there is a significant amount of floodplain trapping, and I will talk about that, and other human influences. And the equation works good in today's world, and we can start with that. So certainly within a factor of 2, 38% of all the measured loads on 488 global rivers. So that's not bad, and there was a blind prediction of 195 of these rivers in that. So for today's world, not bad. And I think you would have to put your uncertainties of application of this, even if you think it can be applied, to take into account perhaps still that we were not able to filter out all of the human influences. This Bogart equation doesn't take at the moment into account earthquake shaking in a very overt way. It's taken into account through a couple of mechanisms, both lithology and relief, but it's still not in an overt way. So that is an improvement we could still make. And earthquake shaking can change yields by a factor of 2, and lithology, as you can see from this map, that can change sediment yields by a factor of 4. And of course, the lithologic map of today is not the lithologic maps of the past. So both the distribution of rocks that are being weathered may indicate that you had either harder rocks, less hard rocks. I don't know. I'm not the geologist you want for this talk, but I can't imagine that this is going to very much represent the rocks of the past, at least as a percentage distribution cover. So I'd like to walk you through this just to give you a sense of where we are in terms of orders of magnitude. So this global range in sediment load is around 7 orders of magnitude for the rivers on Earth. That's 7 orders of magnitude, that's huge. There aren't very many things in the world that have 7 orders of magnitude. One of the influences is the amount of ice cover, and that has an order 1 a factor. If you looked at the factors influencing lithology, that's a factor of 4, so not even an order of magnitude. If you put the world's rivers discharge into this formula, you will, no matter what they are, because of the power to the 0.31, it reduces the impact of discharge to an order of magnitude. So this is part of your precipitation, your runoff, your direct climate input is in this parameter, and it's only giving you a 1 order of magnitude influence. Area is a 2 orders of magnitude, even though it has an exponent of 0.5. Relief is a 2 order of magnitude. So these two, area and relief, still are your dominant factors. And temperature is an order of magnitude factor. So I picked a couple of river systems that I knew had very similar loads, and the Bogart equation, really nailed them in terms of predictions. So they're good rivers to indicate that even with different characteristics, you can have the same sediment load show up. So for instance, the Nile, a very dry, desert-oriented river in the Mekong, same load, one has much more discharge, such as the Mekong, compared to the Nile. The area is so much bigger on the Nile compared to the Mekong. The relief is so much bigger on the Mekong, and you've got these temperature differences, base and average temperature differences, and so yet you get the same loads, and you can see that true for the Colorado River. There's an order of magnitude on the area, but you'll notice the impact of climate now shows up well, and even temperature. And these bottom three, same loads, very different discharge. For instance, the Amur is really high discharge, but it's so cold, it doesn't transport a lot of sediment, even though it has a big area too. So that's the kind of way this model can show up. And so if you were to summarize it, if you had warm rivers, they're going to give you more sediment. And how much more? Typically, a river of the same size, same relief, tropical river gives you 2.5 times more sediment than a similar scale basin in the temperate regions, and 12 times more sediment than a similar scale basin in the polar regions. So I'm going to quickly go through floodplain depressions, the Bogart and river equation in the more broader sense, and a little bit on sediment yields in general. The Bogart is this equation up here. It's a suspended load equation. And if you're predicting what goes into the ocean, it's a wash load equation. It can go down in where you have floodplain sequestration or tectonic depressions. It can shoot up if you have changes in going from a hard rock to a soft rock in your drainage basin. The bed load, it's a slightly different formula, although it's very similar. In fact, there are some bed load experts like Mike Church who thinks that basically the two formulas are almost the same. But it's a local equation where the suspended load is a drainage basin equation. That's the huge difference. So the slope that's in the bed load equation is your local hydraulic head. It's your local slope. Where the relief over drainage area, that's the big slope. That's not the little slope. And you can see that there could be a fair amount of bed load in the mountainous regions of the world, and that load decreases where most of that is either converted over to suspended load or it's sequestered in tectonic depressions. And these tectonic depressions, you know, they're everywhere. And we typically think about, you know, foreland basins, such as in this nice image on the Andes and the Amazon, where you can see, you know, billions of tons per year are trapped in these foreland basins. So significant traps these things can have. But there's all sorts of trapping mechanisms from grabens and half grabens and even very slow developing dynamic topography from mantle flow, crustal cooling. There's salt or mud tectonics in many continental margin environments, and there's folding and other types of isostasy that are going on. So they will impact where sediment gets captured. And we've looked at where these capture points are, and this is just mapping of the floodplains to the 100-meter elevation above sea level. And even just in that small elevation change above sea level, there's all sorts of tectonic depressions in most of the rivers we see in the world. So there's something we need to take into account one way or the other. And to give you an example of what some of these trapping levels could be, in the Yangtze River, the Dongting tectonic depression, you know, it has the capability of trapping like 200 million tons of sediment a year. That's larger than most rivers on Earth. And that's just one of a multiple number of trapping places, locales on the Yangtze River. So they're everywhere. I wrote a paper on this. We need to take this into account. Once these, and depending whether the sediment is pulsed off of the highlands in a way that's sort of at an independent scale, you can either fill up these depressions or not keep up with the depressions. And your loads downriver will change dramatically, basically depending on this fill process. So it's, again, something I think not enough of us take into account. I think because of time, I'm just going to skip this, but we did some work on the Magdalena River and on this particular Mompox depression. It only traps like 14% of the sediment load going to the coastal ocean into the Atlantic. But that 14% can give you centimeter per year level rates of sedimentation in the lake system and the river system that connects it. So you may want to ask yourself, how would the style of these depressions change if you didn't have this vegetation? I think that would be interesting too. And if you were to look at the world again, if we scaled back and look for these hotspots, we do have sediment flux hotspots around the world in terms of latitude. You can see the big one on the Ganga, another one on the Amazon. There's some high ones on the Yellow and the Yangtze and the Mississippi, but a lot of that does reflect human intervention. So we have to be careful when we look at these hotspots. But generally, we have a fair amount of sediment coming at all latitudes, even though we have this unique distribution of landscapes on Earth today. If you're looking at sediment yield, it shouldn't surprise you because of the influence of temperature, and that warm temperatures produce a lot more sediment than cold temperatures. Then if you looked in the colder environments, like in the north of Canadian North, the European North, even Siberia, you're going to have your lowest fluxes. And some of these fluxes are really low, like less than 20 tons per square kilometer per year. The global average is 154. And where you have these high mountainous regions, you can get, areas of sediment flux well over 2,000 tons per square kilometer per year. So yield, highly variable across the world. Highest yields typically are in the mountainous tropical regions of the world, subtropical regions of the world. And when you look at something like the South America, or at least the northern part, in a more blown up way, you can see that some of these river systems that connect directly to the Andes, they're the ones that are carrying the high sediment yield river, where you have many areas that are either draining harder lithologies, such as in this region up here, in the Rio Negro, or they're just literally draining areas that don't have much relief, and you have lower sediment yields. We've been focusing on suspended load. If you looked at bed load, if you look at bed load, these bed load equations, they're just not too bad. They're certainly order of magnitude equations. They could be a factor of 2 or 3 equations. We looked at it in the Mississippi, and it's pretty close, the Bagnode equation to the Nitral dune measurements, or if you looked on the Bagnode, compared the Bagnode to the Restrepo and Kierkegaard analysis. But when you do the bed load calculations along a length of the rivers, bed load goes up and down, up and down, up and down, depending where you get the competition going on between the hydraulic head and the discharge. And so you could go areas that are gaining discharge, and that'll send your bed load off again, or you can get into areas where the very low gradients, and you'll drop your bed load out. So this alternating high and low bed load, you don't see that in suspended load, and again, that's something we all have to keep into account. And just remember, globally average bed load is 6% of the total flux of suspended load. So in today's world, we're very much a suspended load world. Quickly on to just some words of wisdom on, I call miscellaneous. I'll talk a little bit on aeolian ices, bioaerosols, acids, and flocculation. I think this is my one and only slide on aeolian fluxes, and just to remind you all that the deserts of the world show up just pretty much where you expect them to, given the climate, given the trade winds, given the areas that don't have very high levels of water carrying capacity. And in our world today, which is really interesting, you can have 67% of the total sediment flux off the landscape into the ocean is off of a single desert, the Sahara. And it's so dominant, it's really hard to get and to look at this without that influencing all your stats. So it's really hard for us to get good stats that are either reflecting of the latitude or wind structures, simply because of this dominance. On the ice sheets, we're getting much better at knowing what the fluxes are off of glaciers and ice sheets. But just to let you know, the Greenland ice sheet, just the meltwater today is pumping out close to 1.1 gigatons per year. That's equal to the largest river on Earth. So ice sheets can pump out sediment, and of course, during the ice ages, you will definitely have a lot more sediment when they're melting. In terms of iceberg transport, you're not interested in this, but that's many times higher than even meltwater. On rainforest, so you all talked about the world without vegetation, one of the impacts of today's vegetation is that in tropical jungles, they can increase the precipitation by a factor of 2. So if you took that vegetation away, this is, all our models are saying this, the precipitation will decrease. Not a lot, but by a factor of 2, which that can be a lot, I guess. And that's simply because the jungles themselves don't expose much land surface. They're pretty much covering the land surface, and so there isn't a lot of dust-related material in the atmosphere. The only aerosols that you're getting for cloud droplets to form around are these bioaerosols from the jungle itself. And so that factor will disappear in the ancient geological period. Another one that occurs today, and it's a really important one for hot tropical systems, is how the acids form and the bacteria that can survive these bioacids can live in them. And so we have these high humic fulvic river acids that show up like the Rio Negro in South America. And it's very interesting. They just literally will destroy vegetation. And so you might have the bacteria in the past, even if you don't have this vegetation to chew up. But I do believe that there could be some interesting impacts on this lack of vegetation or having vegetation. And comparing the Rio Negro and the Amazon really emphasizes this. You get this temperature impact, you get this change in sediment flux, and that shows up well at these as a density contrast where these rivers merge. And this could be my last slide. So in my early part of my career, I put a lot of effort into flocculation. And it's one of these topics that no one really studies unless you have to, and I had to, so I did. But it dominates how sediment behaves in the ocean environment. And you may want to reflect on this too, and because it may impact your understanding of muds and how muds can travel in the world of the past compared to the world of today. So let me walk you through these diagrams. In this upper left diagram, this is a look at particles suspended in a freshwater plume that's shooting out into over ocean water. And you're in the freshwater core, so this is all 0 parts per thousand. And you can see, I don't know how well this shows up on your screen, but you should see tiny little dots. And that's because this sediment that's entering the ocean is doing so in a very unflocculated way. And in this, oops, let me go back. And this diagram over here, on your upper right, it's basically in about 15 parts per thousand. And you can start to see that the water's clearing up. Still a little hazy. And this is a diffusion haze, double diffusion haze that you're looking at. But you can see much larger particles, and that's the flocks forming. And then in this same environment, just under the plume, 20 meters depth, so you've gone from 2 to 5 to 20, and now you're at 30 parts per thousand, you can see that the ocean water is really clear, except for these very large flocks and these stringers of sediment held together by organic matter, bacteria. And this one shows the camera impacting and throwing up sediment off the seafloor. And here you can have You can see that it's a combination of flocks that are falling, flocks that are being thrown up, but most of the flocks that have already hit the seafloor have already broken up into their constituent particles.
2
So what does
minutes.
this mean for the geological past? Because you can get flocculation in river systems depending on the level of organic matter and bacteria. If you didn't have flocculation, the fine particles would be pretty much able to travel around the ocean before they hit the seafloor. That's a remarkable thing. I don't think most sedimentologists think about that because they live in today's world, not in the world of the geological past, where flocculation is suspect. You may not get much. And so that would be the question you'd have to ask. Do you get a lot of flocculation or not? And how does that impact how fast sediment can settle out of a water column? So I'm going to leave it at that. I'm not much of a geologist these days, but I hope I presented something that you can all relate to in terms of sediment fluxes. Thank you.
Thank you very much. That was a wonderful talk. Most of the final questions that were coming around are pretty much the reason why we decided to compile these talks. In that we've had a range of talks that go from millimeter scale structures all the way to continental scale dynamics that we need to take into consideration. And one of the questions was, how do you bridge the gap between all of these? Now, obviously, that is a question that is a little bit too large, too wide to be answered just like that. But what I would point out is that the work that Professor Savitsky has just shown is, together with Blakely's maps of paleogeography and paleogeographical development, provides a absolutely phenomenal tool for a background for us to think about our river systems. When we look at an individual channel and we only have a depth, or we have depths and widths, or we have plan forms, then we have measurements that we can link to paleo discharge. And I will refer to the work by Holbrook and Wanas about their fulcrum approach, which provides some of that sort of context. I don't know if any of the other speakers would like to comment on bridging the gaps between scales and various aspects of river systems. There is a question for Professor Savitsky. You talked about vegetation affecting rainfall amounts. In terms of looking at pre-vegetation world, what are the vegetation effects most important in the Beakward model, and could they be removed? Can you run the model essentially for a free vegetation-free world?
Can you still hear me?
Yes.
Okay. That's a good question, and so I don't know if there's an easy answer to that, because our vegetation is very climate dependent, and we have climate in the model, so you can't remove the climate without removing the vegetation. There's been some interesting papers that have come online that show that vegetation mediates precipitation. It allows, so when water comes off the oceans and it hits the very first elevations and you get precipitation from that transfer of mediation of water inland, because of the vegetation of today, it allows this water moisture to go back up into the atmosphere, back down again, up and back down for probably 1,000 kilometers longer than it would otherwise. In other words, if we didn't have vegetation, most of the precipitation would be falling along the coastline, and it wouldn't go back up into a system that would be mediated. So I do believe that the precipitation patterns would be different in a non-vegetated world. That would be the first thing to say. On the other hand, the influence of bioaerosols, you probably will have a dusty world. And because you have a dusty world, there will be never any place on the planet that doesn't have the dust for water droplets to form and to aid precipitation to fall out of the atmosphere. So I think that's probably, you would have a greater dustier environment in the geological past than you will today. That would aid precipitation. And so maybe you don't need this bioaerosol in the tropics. That would be my takeaway on that. But can you otherwise work out the impact on biogeochemical weathering? So I don't know. That's not my field. I think that the bioacids wouldn't be forming. That would be one thing, and you wouldn't get these humic and fulvic acid river systems that seem to be dominant in various places on Earth. And if you change the biogeochemical weathering, you're likely going to change the mud production. And if you change the mud production, that probably will impact that formulation. To what extent, I don't know, whether it's a second order magnitude or a first order magnitude, that I don't know. Likely it's probably a second order magnitude.
Okay, there is a very nice final question for us to sort of close this whole scene, which is from Mike Lamb, who is basically asking us whether or not there's any consensus among us as to whether or not the rivers were different before plants. Now we've covered a number of things, and Professor Sivitsky just mentioned that there are indeed changes in terms of the amount of dust and the amount of rainfall. But is there a consensus amongst the people that are studying the rock record whether or not the river systems were different or whether they were not different? Daryl, any views?
I think there are differences. There are also some major problems in time in terms of applying things like the Beauclerk models, because we have no information on relief. And the problem with these lovely formulas, they look really good on modern systems because so many of the variables can be measured directly. In the Precambrian systems, we don't have any. One of the things that maybe will help us get there, maybe to compare the lithology of the sands in the rivers to their discharge, and distance, and climate. We haven't mentioned anything about petrography in this whole session. And I think this is rather important in terms of how we determine a climate signature as one possibility, and how we predict the breakdown of the feldspars to clays in situ that will provide aquicludes for things like CO2 storage. So there's a petrographic aspect of the argument which we all need to develop, in addition to measuring every surface that we can see. We also need to measure group point counts on point section. Sorry, guys.
Phil, any comments?
I think on average, of course, pre-vegetation fluvial systems had differences than present day. And I still go with the preponderance of braided systems, much more sediment in the sand and gravel sizes than the clay sizes because of less chemical weathering. But I also think that as we look more at the Archean and Proterozoic record, we're going to start finding more anastomosing systems and more meandering systems. I think they're there. It's just they're not as abundant. And I agree with Daryl. Relief is something that's hard to quantify for ancient systems, and I think it's one of the things that we're missing. the major control that relief puts on river morphology, channel morphology in particular. I mean, I think of the system that I was describing with the floodplain. That's a very, very low relief system. It's on a delta top, so we know the relief there, and it's got good floodplain development. It's got a good stable channel. The channel's 40 meters thick, and it obviously wasn't 40 meters deep because it's not, well, it might have been, but in that system I don't think so. So it looks like it was stable in one place for a fairly lengthy period of time. So relief does play an important part, but it's hard to get an idea of relief without getting into a circular argument.
Okay. Any other comments?
I found particularly interesting what James was saying about the fact that in a pre-vegetation world we would expect a lot of precipitation along the coasts and less in the interior. James, tell me if I got that right, first of all. Okay, yeah. Does this view consider orogenic effects? I mean, what if we have a good origin in size that is disposed and oriented in the right way with respect to trade winds? Do you think that that would still keep things unaltered, or would probably receive a lot of precipitation?
So it's, it's a little bit of a complicated question, but relief plays an important role in precipitation today, without question. Relief is not a dominant factor on precip in today. It's more the climate belts. This high, in the intertropical convergence zone, the zone around the equator that shifts with the tilt of the Earth, that is just so much more capable of carrying water for two reasons. One, the atmosphere is warmer, and two, the troposphere is so much thicker. And so you can get these, globally, there's just a lot of water that falls under the intertropical convergence zone. And that's independent of relief. In other words, you can get the water falling even in the ocean. So you don't have to have any relief, and you still get downpours. Where you get rainfall on the mountains, where mountains are around, that can influence locally precipitation to get much higher precipitation. So there are areas in, take Papua New Guinea, where you can get 4 meters of rainfall on the mountaintops and 2 meters on the coastal zone. So there's an example where elevation can really matter. But I think for the topic of the day, I don't think that this connection between relief and precipitation is all that important. I think that it's a secondary importance, not a primary importance.
Thanks.
I think we were thinking more in terms of relief as energy in the system rather than amount of water in the system. Energy in the system controlling the sand gravel component of the system, which is fairly dominant in these systems. So like you said before, when you look at modeling the coarser fraction, the bedload fraction, it's more looking at basically looking at the energy regime in that reach. It's a hydraulic head, which then.
Well, I do think that's really important, and in fact, relief is so important for a wide variety of reasons. I wanted to throw one other thing and get you, Phil, and others to comment on this, is that because who was it was saying, I think it was Arnold was giving a talk, and he was talking about the role of groundwater. You'll probably have a lot of groundwater infiltration in the geological past, way more than you do today. Because the river banks and can channelize the water to so much more, it can shoot past some of these drier areas without it penetrating. And if you had a much more distributed amount of water over per square kilometer of the land patch, the amount of infiltration would be very high. So I would like to think that everyone's sort of hitting the same buttons on whether what the role of the channel size and dimensions would be. But if you don't have really high banks that allow the water to shoot across latitudes and climate zones, you're going to get, I don't know, perhaps an order of magnitude more groundwater infiltration.
Okay, thank you very much. I think we're running out of time here, and it was an absolutely fantastic experience, and really lovely to hear all these talks together and have the discussion. I would like to thank the speakers very much. I am extremely pleased that you all wanted to share this experiment and try this out. I thank the attendees for paying attention to pre-vegetated river systems. We will make a recording available online afterwards. I will send it via email to everyone so it can be shared for posterity. Thank you so much.
Okay.
I would like to say also